Is there going to be some kind of counter? Like, you have 10 minutes?
I'll give you a 4-minute counter, a 1-minute, and a 0 and 1.
4, 1, and 0. Okay.
I think there's also time on that. Yes. Yeah. I think it's the Kiva one, yes. Try it out.
The same floor?
Yeah, same.
Should I use this or the...
It's your choice.
Okay.
But you will have to stay within the frame so that they can capture you.
What?
You will have to stay within the frame so that they can capture you.
Yeah, yeah. Yeah, you can hear me right, yeah? Okay, super.
I guess you can start another 6 minutes.
Okay, yeah, 10, 10 exactly. Okay, super. Okay. That's okay. Nice to meet you. Sure.
Joe, we both had plenary.
Yeah, yeah. Yeah, I see you. By the way, great paper.
Oh, yeah. Thank you. Yeah, what can I do?
Yeah, super. Yeah, that was great.
Yeah.
Yeah, I also talked to Matt. He's also
Okay.
doing some things.
Matt was like, oh, we're gonna find you.
Yeah.
I mentioned some book.
You were in the IDTS in March. I was.
Yeah, I was. Yeah. There's one over right now.
Yes, I mean, Mike was there. Talk to him, yeah. Yeah, super. Yeah. I also wanted to ask you some questions about what the Giffre, well, the Vidal gauge is exactly, but we can talk later. In 10 minutes, it's the questions. Time for questions inside the 10 minutes, right?
Yeah, we'll have difficulty within the time.
Okay.
We can stop at 8 or 9.
Yeah. Okay, we'll try. I'll try to do my best.
Otherwise, we'll have to skip questions to the end of the session.
Okay. Yeah. I don't think there would be a.
Tight schedule.
Yeah, yeah, I know.
Hey everyone, good morning. I'm the chair for the morning session. So I guess we can start off with Sergio's talk on Tenet, a composable tensor network library.
Hello, everyone. Thanks. Thanks to all for coming. I will be talking about Tenet. It has been my main project for the last year, and also about some of the related libraries that we have been working about at BSc. So first of all, getting registered in the general registry of Julia is like a speed race. So there is already another library that's called Tenet in the general registry, but ours is not that one. So we have our own registry. So if you want to use these or any of the related libraries, please just use our register. Don't worry, I can pass the slides later. So there have been already some talks about tensor networks. I'm going to give a very brief talk about that. But in general, tensor networks, I'm going to go a little bit fast, but in general, tensor networks are a graphical description of multilinear equations like this one. So for example, here in this graph, nodes are tensors and the edges are vector spaces, are the tensor indices. So this graph is actually equivalent to the equation that you can see in the right. What you can do is, so in order to compute this summation, it will require a lot of for loops. You don't usually do that. You do something smarter. That is that you do the sums in some order, and this order is very, very critical for your performance. So, for example, if we start with M, we just contract the M, and when you contract the nodes, you do perform this operation. This is equivalent to graphical notation to actually sum them, like literally fuse the two nodes. And you can go actually continue recursively until you get one number or another tensor, and this is the number that you are actually looking for. This is a great formulation actually for things like, for example, quantum computing or quantum mechanics in general, but it also, like Matt and other people have been talking about, you can do a lot of other cool stuff. But the problem is that actually looking for the optimal contraction path is an NP complete problem. So it's very hard. And there are a lot of packages right now in the Julia ecosystem trying to deal with this problem, like to expressing all this. Ainsum, Tulio, Interpolation, Ainsum, iTensors. And it's great, there are great packages, but all of them actually assume that the users know like they can type all this equation by themselves. But okay, what happens if you have a graph like this? Okay, you run out of letters, actually. This is actually not very useful to actually type an instrument string like that. So in order to deal with this kind of graphs in large scale, because at BSc we have supercomputers and we are interested in large scale tensor networks, we developed this library that is called NExpressions. That it's inspired in the Python library of the ecosystem. It's inspired in Opti, Ainsum, and Cotegra. They deal with very large tensor networks. The idea behind that is that you can see a contraction path as some data dependency tree. And this data dependency tree, you can see it also as an expression in Julia. So we created our own expression that basically the head is the output indices, and the arguments, the input arguments, are the input tensors or some other n expressions. And with this kind of structure, it's actually very easy to view it as the contraction, like the data dependency of the computational graph. And you can actually see any heuristic or search like an optimizer, and you can also do further optimizations or actually do things like, for example, to use this heuristic till this moment, till you get this depth in the tree, and then use this other heuristic or this optimization. Also, this structure is very useful for getting like results counters, like for example, okay, how much flops I'm going to need to actually compute this, or what are the sizes of the intermediate tensors. So for example, you can do some tensor slicing if, for example, you already have this n expression and you know that it's not going to fit into your node, in your cluster, so you need to slice the tensors. This is like some kind of blocking scheme. And in n expression, we already implemented as an heuristic for searching for them. This kind of tensor slicing, like you see, is actually taking one of the summations of this whole equation and taking it out. Taking it out is not actually doing it separately, it's just doing it, but one of these summations you're going to do it distributively. So you're projecting this index to some basis, and you're copying each of these bases or each of these projections to different nodes, and you run them in parallel. You get an increase, an exponential increase in parallelism. If you choose the indexes wisely, it reduces your memory usage, but also you get an overhead, so this is not free lunch. But it's great for actually getting like easy parallelism. And also, any expression is also thought as a research library. So if you are researching on contraction path heuristics or in tensor slicing search heuristics, it's a great tool to actually see what your heuristics are doing. So this is, for example, before and after of one of these slices. You can see that the n expression is actually much smaller. And so Tenet is the library that actually gets on top of an expression to actually describe tensor networks. It's inspired by QIM and Python library. What is very special and different to other Julia libraries in tensor networks is that we don't have different, like I say, like classes for different kinds of tensor networks. We only have one tensor network structure, and the type of tensor network is actually fused into the type system, into the generic parametric type system. So here, where you see the unsuch thing. And because, like, for example, if you have a quantum tensor network, you need information about sites and about, I don't know, direction. You need some extra metadata, a part of the graph. So you include this also in part of the type system. And you can also inherit this with this metadata and constructor. So it's more or less like the Julian way you have some field inheritance. So this is a very easy way to actually expand the amount of quantum tensor networks that you have, like MPS or PEPs. You can also already have this site information, and you can very easily fuse with an MPS, for example, to have an MPS and an MPS contraction. You don't really need to deal about what are the indices names. Also, another cool thing that we implement, and I think that any other library implements, is local transformations. This is kind of similar to ZX calculus, not really. It's like a numerical thing. In QIM, they implement it a lot. The idea is to simplify the tensor network to get an equivalent tensor network that actually is much easier to look for the contraction path, or you can see for some symmetries, and it's, in general, much easier to compute. And also, we are also very interested in expressibility for our users, because a lot of them are physicists, are not computer scientists. But we are in a supercomputing center, and we actually are very, 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 we care a lot about performance. So I think the best way to use this is to give a lot of freedom, a lot of expressibility, because it's not about doing a tensor network simulation, but about designing experiments. So you should have like good defaults by default, but you should have also the capability to tune the contraction in your own way. So for example, this is the Google Quantum Advantage experiment in less than 15 lines of code, thanks to our care in these kind of things. So for example, you can actually distributively search for the contraction path and also do a contraction of the different slices distributively by just adding a couple of lines. And in the future work, we are actually already have some quantum tensor network implemented, but we want to implement all of them, or all of that are known. We're also interested in some other application of tensor networks aside of quantum tensor network, quantum mechanics, like SAT and combinatorial problems. And for expressions, we are implementing automatic differentiation. It's already implemented, but we are fixing some bugs currently. And also something that would be very interesting about compilable expressions, because this same expression is like some expression, like it should be very easy to actually compile it to a Julia code, or actually using GPU compiler to actually compiling it to, for example, XL, that is the intermediate representation that JAX uses. And thank you all for listening to me. Here in the first line.
Yeah, I have a question about like the distribution.
Yeah.
This is just, you're distributing by just taking tensors, full tensors, and just throwing it to some specific processors. You're not distributing the tensors among the processors.
We're dealing already with that. So the question was about distributing tensors, like the inner part of the tensors. Yeah, this was a very easy example that shows the expressibility. You can do it because we already have tried that with block arrays, so you can use block arrays. And I have already talked to Julian Samaru for using Dagger or these kind of things. So yeah, because the good thing about Tenet is that it doesn't impose you the array types. So you can use any array type. So you put like a distributed array type inside Tenet, it will work.
But you don't have like
Okay. We can talk later.
Please welcome the next speaker, Haik, who's going to be presenting BioSimMD.
Thank you. Cool. Okay. Okay. Hello, my name is Haik, and I work at BioSim AI, where we build tools for computational drug discovery. So I will be talking about BioSimMD, which is one of the things we've built. It's a fast and versatile molecular dynamics library, completely written in Julia. A brief overview of drug discovery. As a first approximation, drug discovery problem takes in a protein target, and the goal is to find a compound that will bind to that protein target and inhibit, for example, some of its functionality that's causing a disease. Typically, you start from a large database of compounds, billions of them, and through stages of filtering, you get to just a handful that will go to clinical trials. So my colleague here actually talked about some of the earlier stages of this a couple of days ago in the talk called BioSimDoc. But we'll be talking about the later stages when you have only a few compounds you want to test, and you can afford to spend large computational resources and do molecular dynamics on it. What is molecular dynamics in this context? So it uses classical force fields to simulate the movement of particles to predict protein ligand binding. In this case, you can see a ligand that's in a pocket of a protein, and we're simulating the process and their interaction as time goes on. So this is a very heavy task computationally because basically every step of this process, we are simulating 10 to the minus 15 seconds of real life time. And nothing interesting happens in that time scales in biology, only some hydrogen atoms vibrate. So to get to interesting processes, you need to do billions of these steps. And bear in mind that at each step you compute pairwise interactions between atoms, and there's tens of thousands of these atoms. So we don't want to leave any performance on the table. So how does BioSimMD's ecosystem work? At the core of BioSimMD's ecosystem is a package MD engine, which contains the core molecular dynamics algorithms. And it relies on a few internal packages we've developed. One of these is, for example, BioSimSimD, which extends the SimD package you may be familiar with. And then we have implemented BioSimThreads, which is a thread pool type of package to manage multi-threading simulations, where we get very good speed ups on multi-core CPUs. We've also implemented a package MDStructure, for example, for allowing us to easily manipulate and iterate over molecular structures. So that's the core of the MD we have, but then there is also application layer where interesting and complicated sometimes computational algorithms, computational chemistry algorithms are implemented. And many of these algorithms, they actually don't run one very long simulations. Instead, you actually need to run shorter simulations, but all of them in parallel. These needs to be coordinated, and they exchange information as they move in that simulation. So to facilitate all this process and this application layer, we've also implemented a package called ParallelMD, which uses distributed JL underneath to spin individual molecular dynamics processes, coordinate them, and so on. So the application layer uses this package underneath. What does this all look like in practice? I've implemented the interface showing here in Jupyter Notebook. So of course we load our package, and then we load a system. In this case, we can load from PDB bank a protein using its code and visualize it directly in the notebook. Then with a few lines of code, we import this system into Biosims data structures that allow for fast molecular dynamics. What we'll here do is actually select the ligand and the pocket surrounding it, and also visualize it. The ligand here is shown in red, and the pocket around it is shown in yellow. Next, we create a simulation out of this object. We set some logging parameters with a few lines of code. And I'd like to bring your attention to this, which allows us to customize, for example, the simulation. We add a spring, in this case, between a ligand and the pocket, and the spring gradually increases in length as we move. So that will push out the ligand out of the way out of the pocket during the simulation. It's just a few lines of customizable code. Then we initialize our simulation and run it, in this case, for just 1,000 steps, because I've run it before in this notebook already for 150,000 steps. We wait for it to finish. The 1,000 steps will be done quite quickly. So now that it's done, we can do quick analysis of the trajectories in logs it generated. So here on the left side, actually we plot the distance of the ligand and the pocket that we saw earlier over time, and we can see the distance increases as the time goes on, which was kind of expected. On the right side, we see the potential energy of this spring during the time. So we see that the potential energy is actually increasing, and then at some point this spring relaxes because the ligand managed to move out of its pocket. So these are the type of things we can visualize and look at in our analysis process. We can also look at different frames of the simulation. Here I visualize the starting frame that you've already seen and the last frame, where we see in blue that the ligand has actually moved out of that pocket, as kind of expected from the plots and the simulation we've set up earlier. So this is a notebook that you'll be able to access in our partner's platform. It's called, the platform is called Deep Origin. So what about performance? I'm reporting here a performance on a system of about 100,000 atoms where we compare BioSim-MD, in this case, on a single CPU core to GROMACS. For those who don't know, GROMACS is a very highly optimized CPU code for molecular dynamics. It's been developed for more than 20 years, I think, has millions of lines of C++ code. And on a single CPU core on exactly the same parameter set, we are faster than GROMACS, and that also translates to dollars per microsecond of simulation. So this may not seem impressive in the first two columns, but imagine you're beating Michael Phelps in swimming. So that's the sort of analogy I would bring here. But on top of that, we have implemented state-of-the-art integrators that aren't present in GROMACS, for example, and these allow us to increase the time step to, for example, from 2 femtoseconds, typically used to, say, up to 10, which gives us extra performance. And then we also have some package to optimize parameters but while keeping the accuracy. So we can actually get to much less dollar value per microsecond of simulation. I can also present some comparison to OpenMM, which is typically a GPU, code base. But the comparison, it's hard to always pick exact parameters that will fit. So we do our best here. To compare, as I said earlier, typically you want to run many different simulations. So in this case, we run 12 simulations on 8 cores each, and per microsecond of simulation, BioSim will be about 5 times cheaper than a GPU code that OpenMM runs. And also keep in mind that, as I said earlier, you want to run many smaller simulations, and CPUs generally are more available than GPUs. So we believe this is the way to move forward. So that's all from me. Please do get in touch for access to the platform. You can have an access like the Jupyter notebook you just saw. And yeah, if you have any questions, I'm around, and also you can email me later as well. Thank you.
I guess we can reserve questions during the session break. So next we have Manuel presenting surrogate-assisted multi-objective optimization with constraints.
Yes. Thanks for having me. My name is Manuel. I'm a PhD student in Germany, and as mentioned already, today I want to talk a bit about this algorithm that we have. It's surrogate-assisted multi-objective optimization for problems with nonlinear constraints. And 2 years back, I already gave a talk on a similar topic. You can find it on YouTube. And basically, this is a short follow-up. And I can give you the short and sweet before. It's basically screw the old code, but keep the theory. And we'll start by looking at a bit of that theory, gloss over some details, and see what we've done so far. So the old package, it was meant to find critical points for multi-objective optimization problems that looked like this with k nonlinear objectives. And then we were also able back then to incorporate convex constraints like these linear constraints here. And what we did back then and what we do still is use these local nonlinear surrogate models for the objective functions. And we do that in a trust region algorithm. And then we don't need derivatives because we have these trust regions in which we have the models. And well, I'm a bit unhappy about how that package turned out. It grew according to the needs of the project that I worked on, and it was a bit messy in the end, and there was still much left to explore, but it never got registered or anything. One of the things that we always wanted to do were these nonlinear constraints instead of like linear convex constraints, which led to the new successor package, Compromised JL. And if you don't know anything about multi-objective optimization, generally it's about finding trade-offs between the different objectives, and then you usually get multiple solutions, which we call the Pareto set or Pareto front, and you can see it on the right in blue. And there's also some necessary condition, which basically means the gradients vanish. It's a bit hand-wavy. You can look into the presentation 2 years back or our current preprint for details. I'll just show some pictures of what we do conceptually. So instead of taking the steepest descent direction, you can use the multi-objective steepest descent direction, which basically is a projection onto the convex set of negative gradients. Now we don't want to take the true derivatives. We use our surrogates and then get an inexact steepest descent direction. And we then have to find some step size by minimizing our objectives along that direction. And because we don't trust our surrogate models too much, we do that within a trust region. And then if our trust region looks nice, is convex, we can project back onto that trust region and minimize along that projected direction in our trust region. And if our constraints are nice, we can just intersect them, project onto that nice set, and handle these easy constraints with that projection approach without too much hassle. But if our feasible set doesn't look so nice, if we have general nonlinear constraints, then we employ our favorite trick. We just linearize by taking the derivatives. And now we're having the same problem as before. We might not have the true constraint derivatives. So our idea was to basically use the same kinds of models for these constraints. And then we use that set within a trust region to find the next iteration site. And if you look closely, this next iteration site must not be, or it could happen that it is not feasible for the true feasible set. And that's why we need a few more tricks, like this filter, which is imported from the single objective optimization literature and which guides our iterates towards the true feasible set asymptotically. We must make sure that our surrogate models conform to certain error bounds, and we know how to construct these kinds of models. And then we can also use them to maybe guess where our feasible set is. And now coming to the code and a bit of the history of our code. Well, we had this package Morbid, which I didn't quite like. And then we had to present some code for the preprint, and what we did basically was copy-paste the most important snippets of code in a Pluto notebook, which was more lightweight and sleek, but in quotation marks, because it still took ages to do all these plots that we did. And what we did was basically just look, does this work? Basically for small experiments. Here we had two parabolas. The critical set is shown black, and we just wanted to see, can we avoid the non-feasible part in red? And indeed we could. And well, the blue line shows that our radial basis functions again worked very well in this kind of setting. We also tested non-convex problems and saw that we could find critical points. But now the reviewers requested more experiments, so we had to actually improve the code. And that's what we're doing currently in the new package. It has a nicer name, a very nice acronym, I guess, Constrained Multi-Objective Problem Optimizer with model information to save evaluations. And we want to make better use of what Julia offers. What does Julia offer? Well, in particular, JUMP and all the solvers it offers are very well suited to the step computation problems that you saw earlier, and it makes it easy and fast to tinker with different descent methods. Then multiple dispatch is just very well suited for this surrogate modeling stuff, and all these autodiff packages also make it very convenient for us to just do some testing in development. And our interfaces internally are designed so that if the need arises, we can hopefully easily interface with either JUMP or some SciML optimization package. Here's some snippet of code that at least didn't error yesterday. So to just show what features are available right now, so we can set our objectives out of place and in place if you want. We have an autodiff backend built in, and we can specify what surrogates to use. And then it does what you saw on the plots, and we now want to do some testing to make sure it really does what we hope it does. What I'm working on is also some graph structure to use surrogate models for certain subcomponents of functions, and I'm also hoping to improve the convergence speed with some nonlinear CG stuff. That's basically where we're at. You can look at the code. It's not registered. I hope to register it in September, I guess. And thanks for listening.
Yeah, thanks for the great talk. Our next speaker is Marco, who's going to be presenting lotterytickets.jl.
Can you help me here before I get set up? I have like a 0% success rate with projectors. Is that good? Cool. Okay. Right, so I'm Marco Cognetta. Today I'll talk to you about a small project that I wrote for something in my PhD that ended up not working out. And then I found a bug in it, and so I rewrote it well after the JuliaCon submission deadline. It's called lotterytickets.jl, and it's about sparsifying deep neural networks that are defined in flux. So yeah, I'm a PhD student at Tokyo Institute of Technology. I work on machine translation, and I also work simultaneously on keyboard language modeling and federated learning at Google Tokyo. And in general, my work and my research and my hobbies are about making models smaller and faster. So this one is pretty much right in my interest zone. So there's a big problem with modern neural networks, and it's that like deep neural networks, as they get, like as they scale up, they basically require too much space and they're too slow. And like these problems are related to each other. And so there's a couple of ways that people have tried to like address this, both the space and the time. And it's sort of like these orthogonal approaches like quantization, where I just, I use lower precision in my model and I can do things faster and it takes up less space, or I distill it into a smaller model, or I use some sort of low rank approximation to approximate some of the heavy lifting layers. And these all sort of work orthogonally, and they kind of do what you would want. They make things smaller, and that tends to make things faster as well. But there's kind of one other approach that I would like to talk about today. And there's this observation that you can make that deep neural models are massively over-parameterized. And the reason for this is like, there are several, practical and theoretical. And one is like they tend to kind of train faster, like per parameter count or something like that. And they tend to be more robust to noise, which is obviously great. But like the most practical reason is that most neural models are implemented as dense matrix operations. And that's really great for like current hardware. And you kind of are okay with paying this cost of like having too many parameters if your training is 1 million times faster, 1 billion times faster, and you can take advantage of like all of the great hardware that we have to train neural models. But if you kind of go inspect a model, you can kind of look and see that many of the parameters are not very impactful. So like this graph down here, I took from a 100 million parameter Distilbert model, and I ripped out all the parameters and I made a histogram, and you can see that it's like extremely heavily weighted around 0. So like almost all the parameters are very close to 0 in magnitude, which means that they're not really contributing very much to the downstream performance of the model. And this may give you a clue to like where we're headed. And so there's this kind of hypothesis, it came out of MIT actually, that is called the lottery ticket hypothesis, that deep, dense neural networks tend to contain extremely sparse subnetworks that account for most of the performance of the overall model. And there's more to it, and there's like other variants of this, but this is the crux of what I care about today. And basically what this is saying is something like I can take a fully parameterized architecture, and I can find a subnetwork, which we call winning tickets, like hence the name. I can find a subtopology of this architecture with like, for example, 10% of the original number of parameters, and it'll be as good or better than the original model, which is like insane. It's going to be extremely sparse. It's not going to be a dense matrix, but it will be very small. And this sort of like already allows things to run on like hyper-resource constrained systems. Like you can't run extremely heavy models on cell phones or drones or toasters or something like that. You need it to be small. And so lotterytickets.jl is sort of supposed to help you implement this. But how would you find a lottery ticket? This is actually like a really hard problem, but there's kind of a simple heuristic that you can use that's described in the main paper, and it's been like kind of expanded upon. And it's kind of this like extremely embarrassingly simple loop. So basically you start with your model and you train it to convergence, and then you like select the bottom X%, like 10% or 20% of parameters by magnitude, and you just remove them from the model. And you reset the model to its initial parameters, not like you're not fine-tuning, you're like starting over. And you repeat again. And you do this until either like you reach the desired sparsity level or your model performance begins to degrade. And so lotterytickets.jl is like the package to basically give you the tools to do this easily with your own Flux model. So it pretty much provides like two things that I want to talk about today. The first one is really the key thing is prunable layer wrappers. So pretty much for all the Flux layers, we provide a wrapper, like an analogous prunable type. So if you had a dense layer in your network, you would instead use a prunable dense layer. And we also have like this easy interface that if you come up with your own layer, you can make it prunable in the same way that ours are, and hook into all of our machinery. And it basically tries to mimic sparse matrices and gradients. So like when you're pruning models, you're sort of removing these from the matrix, but you're not setting it to 0 really, you're like structurally removing it. So we have to kind of take care to do that. And the second thing that it implements is a group of pruner types. And these are like basically what tells you actually how you should prune a model and which parameters should you be looking at collectively to prune. And like the main one that we implement here, there are others, but they're not included in this library, they're not really related, is a magnitude prune group. So it's like it takes a group of layers and it collectively prunes them by some magnitude according to a percentage threshold that you would care about. And so I'll give a brief little like introduction to the underlying code. And the key thing is this prunable layer wrappers. So they thinly wrap like the layers of a Flux model. And the idea is that we want to wrap it and we want to capture and mask gradients in order to mimic sparse matrices. So in the forward pass, I have a prunable layer here, and inside of it there's a regular layer. And there's also a series of masks that can mask out the weights in the regular layer. And there's also a series, like some original initialization weights for when I need to rewind it during the lottery ticket loop. And so like when the inputs come in, I send it to the layer, and maybe I apply the mask to the layer to like make sure that what I'm looking at is really like all the zeros are zeroed out. And I pass it forward, and it kind of goes through the network as you would expect. But on the backwards pass, when I get a gradient, the gradient comes into the layer, but before I pass it on, when I compute the new layer, I have to send it to the masks. And the masks mask the gradient so that these like parameters that have been removed don't contribute gradient information to anything else. They don't get propagated up the chain. And so this is basically the whole library is this way to capture and mask gradients in a nice manner. And one may ask, why are we using masking versus sparse representations? And there's two reasons for it, pretty much. One of them is that until you get extremely, extremely, extremely sparse, doing this masking and a dense matrix multiplication is like orders of magnitude faster than doing a sparse matrix multiplication. And the second is that when you're doing gradient updates, when you're doing weight updates, you can very easily like accidentally broadcast an add or something like that to a sparse matrix, and then suddenly the whole thing becomes dense, and like your training time goes up by 500x. So that's why we would do it this way. And here's a quick like example of how you might use this library. So on the left-hand side, I have like a simulation loop of how you would do the lottery ticket hypothesis, and I have a regular Flux model, this chain. And I just have prunable dense layers in it. And I have some dense layers and I have some LSTM layers. Like every Flux layer is supported, and you can mix and match prunable and non-prunable layers. You can do whatever you want. And also, it works on GPU, it works on CPU, doesn't matter. And then I define a series of pruning groups. So I want to prune like the first two layers of this model together with 20% of them going away. And I want to prune the last one and by itself with 10%. And then I put it in a pruner, and then I run this loop where for however many training rounds I want to go for, however many pruning rounds, I train the model to convergence, and I prune and rewind the weights, and then I start again. And at the end, I sparsify it. This produces a sparse representation of the model, and I'm done. And I have this kind of nice little syntactic sugar over here where I can just like, you can define a Flux layer as normal and slap a prunable macro in front of it, and it will produce the prunable model for it. Here's a few interesting projects that if you're interested in this idea, you might like. This is the original paper on the idea and a Python library written by them for implementing this. And there's another one about iterative pruning that I didn't know about called tinynets.jl. It does something similar to what we do. And then there's a paper here about a stronger version of the lottery ticket hypothesis. And actually, the authors use Julia to implement their experiments. So it's kind of nice. And then finally, there's an MIT course about efficient deep learning that basically surveys this entire field if you're interested. And finally, the repo is on the left, and my personal site is on the right. Thank you.
Thank you so much. We can have questions during the break. So our next talk is by Pierre about an optimization package for constrained nonlinear least squares.
All right. So I'm going to talk about the Julia package in the code ENRSIP, which stands for Easy Nonlinear Square Inequality Program. Basically, this is the Julia version of a Fortran 77 open source optimization library that was conceived in the 80s by two Swedish authors. And to give an overview of the mathematical method implemented in that package, it's a Gauss-Newton type method applied to nonlinear square with an active set method to handle the constraint. So the question that you must ask is, why would I present the Julia version of a Fortran library? Well, it's because in my research, I was in close collaboration with Hydro-Québec, who's, to give an overview, the biggest producer and supplier of electricity in the province of Quebec in Canada. And they use a ton of, and they need software to calibrate their forecast model in order to know how much electricity they need to supply. And so they use a bunch of different solvers in order to calibrate their model using all of the data that they own. But the thing is that it's a kind of a system where it's used in such a critical environment that you don't want to change it as long as it's working. The thing is that until it doesn't work. And so it's been used for a few decades now with Fortran models and Fortran solver, but it's less and less adapted to the current need of Hydro-Québec, and so they are slowly started to moving from Fortran to Julia, and one of the first step that they wanted was to convert their optimization library into Julia. And they also started a lot of projects to make some interfaces between Julia and Fortran in order to use Julia solver, but with to optimize functions written in Fortran. If you want more detail about this, there was a talk yesterday about how Hydro-Québec is doing this, starting this transition. So back to the math, and so basically this is the general form of the problem solved by our package. So this is a nonlinear typical form of nonlinear square under, as you see, a general constraint. The only thing that we assume on the constraint and the residual function, the function inside of the norm, is that they are nonlinear and non-convex. But that's all. We make no assumption on box constraint linearity. So it remains a very general formulation, and that's why we thought it was interesting to use this package, even though the method implemented is kind of old. So just to give some details on how to use the package. So first you need to instantiate a model. We're not connected with Julia interfaces as jump or other. It's in plan for the future development. But basically you need to pass the dimension of the problem, the evaluation function. If you have any bound, it can handle box constraint, of course. But yeah, and for the Jacobian, since it's a method using Jacobians, you can either pass the analytic functions or just say that you want the algorithm to compute them numerically for you. And some optional arguments that I don't want to get in detail. So to give an example with a simple 3-dimension problem, let's say here I first compute my dimension, then define the residual and constraint function. It has to be, even if there is only one constraint, it has to be in an array for the use of the package. But of course, you have more constraint, it works well. And then just vector of lower bounds. Then define my Jacobian, since it's a very easy problem, it's not hard to do, but you can use your favorite automatic differentiation package, of course. Just give a starting point. Instantiate my model with all this bunch of informations, and then just call the solver, and I set the solver to silent, but if you want an output and some detail about the iterates, this is an optional argument you can modify. So this is just a table with some results that we got and compared with a nonlinear optimization solver called IPOpt. So just to see on some problems, some very easy problem with probably a known global optimum. So IPOpt doesn't outperform for this kind of easy problems. I didn't print the performances, the benchmarks for the time of computation, because there is not enough room in this slide, fortunately. But globally, our software isn't like as optimized as IPOpt, but it was okay in terms of time of compute, CPU time. So to conclude, this package can be, I don't think now, there's a package manager, I tried this morning, it doesn't work, but you can download it using the GitHub repository. And I recommend to check because you can see there's some documentation for more details on like how to use the library on some more examples. And just a quick word on what we are planning for the future. So we are aware that the way to implement model is very specific to this package, so it's not very practical. But we kind of aiming at some compatibility with Jump would be great. But we're also, like, for the short term, we might also target compatibility with optimization API and especially NLP models. So we don't know which is a nice way which would be a nice way for us to model in a very general way non-linear square problems, and would be great for a benchmark. And I printed you my email in case you want to make some feedback, and anything is welcome. Thanks for your attention. For nonlinear problems in general, this solver is targeted for problems of this form, so it can handle, like, the objective function has to be of this form. Yeah. Yeah. I mean, like, IPOpt isn't designed for least square, but it's just for IPOpt, it's like a special case of use. But we just used IPOpt because it was like a state of the art and like one of the most efficient nonlinear fuzzer. But it's also like what was interesting for us was more solver that could handle general constraint more than the least square term. Since there are a bunch of solver for least square problems, but with this kind of constraint, it's still kind of a niche in a way of speaking. What do you mean?
What is the size of the dimension of the problem you try to solve at
Quebec? There could be some industrial information. Not sure I can tell everything, but it's like, I mean, a few hundreds of parameters, around 1,000, something like that, with same number of constraint approximately. Still relatively small, I would say, but the number of constraints can be quite as much as the number of parameters, which is, I mean, as I said, the least square power ending means something, but it's more this handling of the constraint that's really why they use this solver in particular, and why they've been keeping it for many years.
Thank you so much, Pierre. So our next talk is on fast OP interpolation.jl by Nicholas.
Yeah, thanks a lot for coming. I want to present a package I wrote with Eduardo Grossi together a couple of months back. And so, as the name suggests, it's about interpolation, and it's about interpolation with pseudospectral method on certain domains I'm going to explain to you. So, first of all, maybe the question, why another package? I guess the fast Chebyshev interpolation package is relatively common, and it was also our inspiration to write this. The simple reason is we wanted essentially the same things, so pre-calculate a lot of functions and evaluate them even more while maintaining full flexibility and control, so manipulate everything essentially whenever we want. But our big problem was that our domains are not hypercubes or hyperrectangles, meaning unfortunately we can't use this package, but we need different geometries. So to give you a very simple example, where this is relevant for us, so we typically encounter equations that look like this. So you have some objects, and then they appear in integrals on the right-hand side. We have to calculate adaptively. And then these domains of these variables in the end turn out to be cylinders, prisms, tetrahedral lines, or something like that. And then unfortunately, we don't only have like such a small system in reality, but we have like hundreds of equations with like thousands of terms inside the integrals on the right-hand side, which is why we want to interpolate. So how does it work with pseudospectral methods? So we pick up via collocation, so we pick up a bunch of points here on the function and calculate our function there. And then we want to represent simply this usually expensive to evaluate function with some polynomials. Orthogonal polynomials are nice because in a sense they're optimal. They give you spectral convergence, meaning if you add more points, you exponentially get better in representing the function you interpolate. And then the big task is here to represent your function simply by a bunch of coefficients and then your polynomials called phi here. And given that you have here some nodes xi where you evaluate everything. So you can simply rewrite this as a matrix problem, like your function equals some matrix times your modes. So in order to access these modes, the big question, the only task essentially is to invert this matrix. This is a rather well-known problem. These matrices are called Wonder-mode matrices and are simply the polynomials evaluated on the nodes where you know your function. And this immediately determines where you actually want to evaluate your function, because if you just pick equally spaced nodes, for example, like equal sampling, the conditioning of this matrix diverges exponentially, so you can never invert this matrix for a reasonable number of points. But if you pick up different points, for example, Chebyshev points in one dimension, it only grows logarithmically and you can invert huge matrices easily. Then to evaluate this, you can evaluate arbitrarily high orders of orthogonal polynomials as stable and extremely fast. So they have three-term recurrence relations, which you can just unroll internally. So you scale linearly with the degrees of freedom, which we also tested up to a couple of 100,000 of degrees of freedoms in our code. And then everything is floating point stable. So floating point errors never accumulate in these relations. And one nice thing is in all of this business, it factorizes over geometries. So if you combine geometries to some larger dimensional geometries, everything factorizes. For example, if you have two of these Wonder-mode matrices which you need to invert, there's a Kronecker product in between, and then inversion simply, well, you have to invert them individually, meaning you only ever deal with sort of medium-sized geometries. So what's currently implemented in the package, there are 3 base domains available, a line, so the most common one, I guess, then triangles and disks. And then we have essentially large classes of polynomials for all these geometries. So in a line, you can just pick up any Jacobi polynomial you want, so Legendre, Chebyshev, and all the others. On the triangle, it's currently Kornwinder type 4 polynomials, and on disk, Kornwinder times 2 polynomials. And the package provides you already nodes for line arbitrary order, and for a triangle up to order 18 of the polynomial, which, for example, you can see here for some lower order of the polynomial, how they are spaced, so always towards the edges of your domain. And the same for the disk, where they are known up to order 30, and they're giving in big float notation also if you need that in your applications. Then you can combine these domains in arbitrary fashion as you want. So if you need these such interpolations on, for example, prisms, you just take a triangle and a line. For a cylinder, you take a line and a disk. You can, of course, build hyperrectangles, but you could also build more crazy stuff. So you can combine lines and 2 disks, for example, to build something 6-dimensional, unfortunately, which I couldn't visualize. How do you use it? Well, it's extremely simple and straightforward. So let's say you have some function. You simply define your domains. So you have to specify corners. All the mappings are getting done for you internally to map everything to reference elements. Then you set up your interpolation element by simply combining these. It returns you an interpolation object and then the nodes where you should evaluate your function in each domain. You can also, for convenience, directly give you the tensor product of your nodes, which then become large matrices. And then your typical loop would be you evaluate your function on all of these nodes simply. Then you call a single function called update interpolation. And it carries out the internals. And then you can simply call this your interpolated function as much as you want. And in this case, for example, if you have some simple function, something like a sinus, of course you reproduce it exactly, even with like moderate-sized polynomials here. So what's to come? More base domains, of course. This will be very soon because I need them for my personal research. So tetrahedra and spheres, to just name 2. The other big thing we are working on, which unfortunately might take a bit longer, is currently you can't use autodiff in this entire setup to produce derivatives of your evaluations, because the performance comes from using internal buffers to unroll all the nested recursions that appear in these polynomials, but we're working at that. And if you have any feature requests, like more polynomials, or want to participate in any way, please just contact me. Yeah, thanks a lot.
Thank you so much. Any questions? We have time for a couple.
Do you think it would be straightforward to do it?
Yeah, that should be possible, actually. So the problem with these domains is always a bit, polynomials have to be known on these domains. So if anyone ever figured out polynomials for these domains, then it's no problem.
For that sine function example, did you compare the speed of the sine function versus the interpolated function?
Not systematically, because you would need then to figure out sort of it's not our use case to represent simple functions, even simpler in a sense, but to reduce it for external, really expensive. Yes, exactly.
Anyone else? Okay, thank you. We will break for 20 minutes and we'll be back at 11:20.
That's 10 minutes.
Oh, sorry, 10 minutes, yeah.
that the slide appears here. But,
Oh, okay. So I think display. Yeah. Okay, so I can just measure it.
Okay, fantastic. Yep, it works. Thank you. Okay. Yeah, I mean,
Yeah, that's fine. Yeah.
what most people are using, yeah. Yeah.
flags, it's HDMI or also USB-C? Okay, I have also, otherwise I can plug it in here. Okay. So, yeah.
But I think you can directly put it in. No?
Other side. On the other side. If the screen shows up, I think it's okay. Yeah, it looks good.
Yeah.
Cool.
Yeah. Good. Thanks.
Okay.
I think it will be faster if they restate. If for any questions, please restate before answering.
Yep.
We can start off in like 30 seconds.
Okay. Hello everyone, my name is Luca, and today I'll be presenting the role of unknowns in Julia UDE modeling. So this work was done in conjunction with Dr. Giulio Dalla Riva as my supervisor. So before we begin, we first need to talk about universal approximators. So what are universal approximators? Universal approximators are objects that are able of approximating any function to some parameter size limit. So examples of these are Chebyshev series or Fourier series. And it turns out, according to the universal approximation theorem, that any sufficiently large neural network with nonlinear activation functions is also a universal approximator for any Rn to Rm function. Okay, so now that we know that, what is a universal differential equation, or UDE? So a UDE is a differential equation of the form du over dt is equal to some known function, so some mathematical expression that we know, plus a universal approximator, which in our case is this neural network. So why do we even have UDEs in the first place? Well, suppose we have some data, and we want to find a model that represents it, that models that data, right? We want to find a differential equation that can model that data. And perhaps we have some information about that system. Perhaps we know it's periodic, or we know there is exponential growth. So we want to include that information into the model, and we do so via K. However, by doing so, we may not get a perfect fit to our data, right? There may be things that there are like underlying mathematical things going on that we're not encapsulating with our known function, and we use a universal approximator to figure them out. But this leads us to another question. What if k, that we previously described before, what if it's incorrect? So what if we specify something mathematically that's not supposed to be in the model? Can our universal approximator, or neural network in our case, find that mistake, and can it correct it? So here we have a little example. So we generated data from the following system, Lotka-Volterra system. So we have that here. And so if we have correct specifications that we have up here, we can see that we have a really good fit when it comes to predicting data into the future. But when we include a wrong specification, so here we use K1, so this is the first, so instead of using U1, we used 0. This is a typo here, it should be 0.2 plus 0.8 times U1. And again, if we use an incorrect specification for this equation right here, instead of using minus U2, we use 0.2 minus 0.8 U2, we get an equation that is slightly off, right? It's not quite it's not quite a perfect fit. So before we get really into it, let's talk about the methodology of this experiment. So how did we even go about conducting this experiment? Well, first we need an ODE, right? So we generated this with the following Lotka-Volterra differential equation, and we took data at a time step of 0.1 from 0 to 5, right? So this is the data that we generated. This is our true ODE. And then we define our UDE. So how did we define our UDE here? We have this kind of parameter A here that is a parameter that we can adjust to make our K more incorrect per se. I know it's not a great way to phrase it, but if A here is equal to 1, this function 1 here gets eliminated, and we're just left with the correct specification. And as we make A larger, we get a more and more incorrect specification. So we vary this parameter A, and then we train the UDE, right? We train the neural network, and we get a model. We then use symbolic regression, SINDI, to get back a symbolic expression of our differential equation. And I should reiterate, we don't perform SINDI on the entire model per se. We just perform SINDI on what the neural network does. So only on this part right here, right? Only in the unknown part is where we perform the symbolic regression. We don't perform symbolic regression on the whole model overall. And this is important because you'll see that the results we get are indicative of this. So anyways, we train the model, we perform symbolic regression, and then we make predictions from 0 to 10, again, at a time step of 0.1. We then calculate the sum of the absolute differences of our UDE and the original ODE from which we got the data, and we add them together from 5.1 to 10, again, at time steps of 0.1. So this is to model accuracy, right? How well did we predict the future with these equations? And so finally, we get to our solutions. So here we start off with just varying A with our function of U1 and U2 being 0. So as we can see, when we vary A ever so slightly, we get very odd results. So we got so if we look at no error whatsoever, we get a very good fit, right? And even varying A slightly, we start getting crazy results. So basically, moral of the story is no. If you have incorrect specifications, your UDE won't necessarily be able to fix those mistakes. And again, I want to reiterate, they could be fixed if we applied symbolic regression on the whole model instead of just what the neural network finds. So I just want to reiterate, perhaps we could get different results and perhaps better results if we did perform that way. But unfortunately, with the way we had conducted the experiment, the answer is no. We got horrendous results. However, it's not all bad, as we can see. Over here, we have decent-ish results, decent fit. And actually, this is the example we have right here. So as we can see, it's not entirely bad, but again, it's not entirely good either. And then finally, we have unbounded. So basically, this is our solutions just shot up to positive or negative infinity to the point where basically our solutions were unbounded. We got crazy results. And yeah, so these were the results we got. Thank you very much. That's all I have for today.
Any questions?
So I was a little confused about the setup that, and I'm sure this is just not
Yes.
It seems, without having a deep understanding of it, it seems like you would be training the neural network to learn the additive term.
Well, you're training the neural network to kind of try to cancel that term, right? So let's say, let's say we have, so let's look at this example right here. We have, so for anyone wondering, the question was if the neural network, if we give it a wrong specification, would the neural network learn the wrong specification? And so the answer to that is ideally no. So here we have a correct specification, and so we want our neural network to find this term right here, right? So if we give this specification here that is incorrect, ideally what we want the network to find is this term here, then we want it to minus 0.1, and we want it to add 0.2 U1, right? So we want it to make that correction. But the problem is, it usually does a good job. So if you train the UDE numerically, usually the result is okay. The problem is when you then do the symbolic regression, since we're only doing the symbolic regression on the neural network, the incorrect term stays in our equation. So that's why I was saying it's important that if you were to perform symbolic regression, you perform it on the function as a whole, because then in that case, you might actually get rid of these terms here. But yes, with the way we had conducted the experiment, that wasn't the case. Yeah. Any other?
I'm sorry.
Yeah.
Is it a limitation of the neural network learning? Is it a limitation of symbolic regression? Is it like because of the order that, like what is the...
The error usually was with the symbolic regression. So the neural network as a whole, they're not great when it comes to predictions, but they're really good at like getting a really good fit for the training data. They're not really good for the testing data necessarily. But with usually the problem is with the symbolic regression, because the symbolic regression, that's when you start getting like, you know, you start getting terms that are relevant, like your coefficients of U1, your coefficients of U2, et cetera, et cetera. So yeah, it's a bit of a mixture of both. For most of these experiments, we got a really good fit on the training process. Only I think on like one case of the unbounded, like instead of 10 to the negative 6, it was like 10 to the negative 5. But like we got really good like losses overall. Yeah, if I had to guess, I think the mistake is more to do with Cindy more so than it is with the neural networks. Yeah. No worries. Oh, yes.
So like for Cindy, you have this sparsity parameter.
No, I haven't actually. Sorry. Yes. We didn't adjust that parameter. No. We stuck with I think it was 10 to the minus 3. 10 to the minus 3 or something. But yeah, no, we didn't play with that parameter. So again, yeah, absolutely, playing with that parameter. And there's a lot of things that actually can be varied here. So it's not, this isn't like an experiment to say this is, how it is. It's more as like an indication of like, these are things you might want to consider next time you want to do the experiment or, solve a UDE. Yeah. Thank you.
Thank you so much. So the next talk is by Julian on differentiable isospectral flows for matrix diagonalization.
Yeah, thanks for the introduction. My name is Julian. I'm a PhD candidate at the University of Basel in Switzerland in a quantum theory group. And today I'm going to present you a differentiable implementation of isospectral flows for matrix diagonalization, which is joint collaboration with the with the Julia lab here at MIT. So a key problem in numerical analysis is the design of stable and efficient algorithms for solving eigenvalue problems, so for finding eigenvalues and corresponding eigenvectors. And in this talk, we're going to focus on the diagonalization of Hermitian matrices. And for Hermitian matrices, this essentially boils down to applying an appropriate unitary transformation U, such that after the application, we end up with the correct diagonal matrix. Now, typically, we perform this transformation in an iterative fashion, and here L denotes this flow parameter, which labels each of the iterations. And what we want is that as this iteration number L goes to infinity, we end up with the correct diagonalized Hermitian matrix. Now, traditional methods such as Jacobi's algorithm or QR algorithm perform this transformation in discrete steps. So here L is an integer number.
Now, if we take the continuous limit, so we let L be an element of the positive reals, we end up with what's called isospectral flows. And here, isospectrality refers to the property that the spectrum is the same, so the matrices have the same eigenvalues throughout this flow. Now, an isospectral flow is governed by the following ODE. So here we see that this Hermitian matrix H evolves according to an ordinary differential equation with respect to this flow parameter L. And on the right-hand side, we have the commutator between what's called an anti-Hermitian generator and the Hermitian matrix H. And in principle, we are free to choose this generator eta however we like, as long as it's anti-Hermitian, and this will result in an isospectral flow. But in general, we only know two classes of generators which have provable convergence, so for which we know that if we let this flow go towards L, we let L go to infinity, so we solve the ODE towards its steady state, we end up with the correct diagonal matrix. And these two classes differ in how the off-diagonal elements evolve over the flow. So on one class, the norm, the L2 norm of these off-diagonal elements is going to decrease monotonically over the flow. An example of this is what's called the Wigner generator. So here you see the matrix elements of this Wigner generator eta, and note that it also depends again on this Hermitian matrix. In the second class, there in the second class, the off-diagonal elements are also allowed to temporarily increase. An example of that is called the Toda generator. Now, in general, different flows induced by different generators also have different properties, such as stiffness, or they differ in the number or nature of the fixed points, or how they preserve different sparsity patterns. So as an example, let's consider this 2x2 real symmetric matrix, which has essentially two parameters, which is the W on the diagonal and omega on the off-diagonal. And here you see the phase portrait for the Wigner flow, so the flow induced by the Wigner generator on the left and the Toda flow on the right. And you see that in both cases, the phase portrait, or all of the trajectories in this phase portrait have this circular shape, which comes from the fact that this flow really happens on an isospectral manifold. So it's analogous to rotations in complex space. And you also see that they differ in their fixed points. So in green, you see the line of stable fixed points, and in red, the line of unstable fixed points. And if we now pick sort of an initial Hermitian matrix, so initial values of W and omega, and let this flow run, we see that it evolves towards this line of stable fixed points, where omega is equal to 0. So the off-diagonal elements are 0, and we end up with the correct diagonal matrix. Now, for a given initial matrix H, we can solve this flow using ordinary diffie-Q. Note, however, that standard ODE solvers do not preserve isospectrality. And so it's better to use geometric integrators. So you might be familiar with a special case of a geometric integrator, which are symplectic integrators, and those respect energy conservation. And in our case, we are concerned with conserving the eigenvalues or the spectrum. Now, isospectral flows take up a special role in quantum physics. So the properties of closed quantum systems are described by Hamiltonians. So Hamiltonian is simply a Hermitian matrix whose dimension, or square Hermitian matrix, whose dimension grows exponentially with the number of constituents. And these continuous isospectral flows allow one to, in a very elegant way, introduce approximations which enables the analysis of larger systems. So I don't have time to go into the details, but I just want to sketch the key idea, which is that one expands the Hamiltonian in a suitable operator basis, and then truncates this expansion and simply flows the remaining coefficients. So here I'm showing you this for the example of a qubit. So the qubit is described by, now it's a Hamiltonian, the same matrix you've seen before. And here we can do an exact expansion, so we don't have to introduce any truncation error. And we can expand it in terms of Pauli matrices, sigma c and sigma x. And then here the two parameters are this W and omega. And once we plug this Hamiltonian into the commutator with the Wigner generator, we can derive these two differential equations which cover the evolution of these expansion coefficients. And if we solve these differential equations towards their steady state, so for L going to infinity, we can plug those values back in and end up with the diagonal Hamiltonian. So that's the general procedure of applying this method. Now, if we introduce these approximations and flow these coefficients, that will lead to some restrictions. In particular, we cannot access the eigenstates anymore because we are sort of restricted into this reduced subspace, and as soon as we leave it, this computation becomes intractable. But there are still a number of forward problems which are compatible with this procedure. Namely, we can still calculate all of the energy eigenvalues, and more generally, we can calculate expected values of physical observables in eigenstates or thermal states, as well as time-dependent expected values. And now, differentiable implementation could, based on these forward problems, enable a number of interesting tasks. For example, we could compute differential physical quantities, we could perform parameter estimation, inverse Hamiltonian design, or it would allow us to seamlessly integrate this isospectral flow method into other scientific workflows, such as the design of quantum controllers. Now, how does one differentiate an isospectral flow? So there are different ways to go about it. Sort of at the most basic level, we could just view this isospectral flow as a generic Julia program and directly apply automatic differentiation on the base operations. So in our case, the operations of the differential equation solver. But if we put in a bit more structure of our problem, so for example, by noticing that we are solving a system of ordinary differential equations, we could use the continuous sensitivity analysis algorithms embedded in SciMLCensitivity.gl. And if we go even further and put more structure into the problem, we can do this by defining custom forward and adjoint rules, which is made really easy with chainrules.gl. And there we sort of take two different routes. So one is based on applying the implicit function theorem on the steady state condition. So recall that in the end, we're only interested in taking derivatives with respect to the diagonal matrix, which corresponds to the steady state, and not really about the derivative at intermediate stages during the flow. But here in this isospectral flow method, we have an additional constraint that ensures isospectrality, and that's why the steady state rule, which is implemented in SciML sensitivity, doesn't work out of the box. Then a second approach would be based on formulating the eigenvalue problem and applying perturbation theory. And in this case, we have to be careful not to include any computations which involve the eigenstates. So we know that we don't have access to the eigenstates, or else if we do, then it's going to be intractable. So we have to formulate this method in a way which deals or only uses this limited information we have when flowing the expansion coefficients, so if we do these approximations. Yeah. So as a toy example, we can again consider our qubit, and for example, we can compute the differential physical quantity, which is the specific heat, which corresponds to the second derivative of the free energy with respect to the temperature. Another example would be to perform inverse Hamiltonian design. So here we optimize the expected value of the magnetization in the ground state as a function of the external field strength omega using gradient-based optimization. Yeah, with that, I'm at the end, and as an outlook, we are currently working on applications to large quantum many-body systems and performing benchmarks. Thanks.
Thank you so much. We can have questions during the break. The next talk is by Frank on differentiation of discontinuities in ODEs arising from dosing.
Yeah, I will talk today about the differentiation of hybrid systems. Hybrid systems are a bit more complicated than standard ordinary differential equations, so it's important to first understand how you would differentiate actually ordinary differential equations. And the first important aspect is, why do we actually want to do that? And so typically if we want to solve some optimization task or some parameter inference task, maybe we want to calibrate our model to some data, then we, well, if it's high dimensional, then we want to do gradient descent to solve these optimization problems. And to compute the gradient, well, we also need to differentiate through this differential equation system. And so an ordinary differential equation is defined as this equation here, where we have a vector field f that can depend on some parameters. Y is the state of the differential equation, and we have an initial condition at some initial time, t0. Then, depending on our problem at hand, we encode the objective in form of a loss function, which might look like this, so where we have some instantaneous loss that depends on the state, so on the solution of the state of this differential equation over time. And then we are in the end interested in computing the gradient with respect to the parameters or with respect to the initial condition. And typically the important questions that we first have to ask are how many parameters do we have? That decides if we want, whether we want to use something like forward mode AD or reverse mode AD. And we need to consider the stability and the memory properties of our system. And there's not time to do a very careful introduction to sensitivity analysis for differential equations, but to give you like a rough picture of this, is like the basically easiest way to do sensitivity analysis is to write all your differential equation solvers in a DSL that's fully compatible with automatic differentiation, and then you just call your AD package on your solver operations. That's typically hard to maintain though for like very complicated solvers, so not every step in the solver is immediately differentiable. And then you resort to some other things like continuous sensitivity methods. So continuous sensitivity methods, for example here continuous forward sensitivity analysis arises when you just differentiate the previous differential equation, and then you can propagate the sensitivity of the state with respect to the parameter in lockstep to this primal solution of the ODE. There's also an adjoint version for that problem, which scales efficiently with respect to the number of parameters, where we very similarly get a set of differential equations, where lambda here is then the adjoint state. And the first thing that you might notice here is that in this kind of differential equation here for lambda, you see that there are these vector transposed Jacobian products, which is a typical sign that you do now something in reverse mode. And the slightly complicated part here is that this second differential equation you have to solve in reverse from a terminal condition. And at the same time, these vector transposed Jacobian products depend on the state of your forward evolution. So you kind of need to recompute the state to compute this adjoint solution. And the third equation here gives you the gradient with respect to the parameters. And you actually notice here in this equation that there's no lambda theta on the right-hand side. So this can be also solved as just an integration problem. So if you ever wondered how these different continuous sensitivity methods in SciML arise, those are just different ways to solve these two problems, recomputing the state or solving this integration. And they have then different stability properties depending on how you do that, and also different memory usage kind of requirements. And in this talk, we basically discuss now the extension to treat discontinuities that usually are implemented in terms of callbacks. Discontinuities, if you're not familiar with that, can arise from two different sorts of events. So first you have explicit events, which are sometimes also called discrete events, which depend only on time. So ahead of solving your differential equation, you can basically compute all your event times, and then you just set stopping times in your solution, and then at these points, some event will be triggered. The slightly more general type of events are called implicit events, where the event condition depends not only on time, but also on the solution of your differential equation. And there's two small examples for like what can happen at these kind of condition functions. You could have, for example, a piecewise constant controller that's only updated at specific time points, or you can have, depending on some concentration in your system, some bursts that spikes. The rough general idea of what you have to do in solving for your sensitivity equations is basically that explicit events, it's rather easy to understand it. So because we know these kind of events times ahead of the solution, the problem decomposes into solving before the event time, then solving through this kind of effect function that we apply, and then again solving for after the effect function. And what we do is then we update this adjoint solution where tau j minus here is the left limit to the event and the plus indicates the right limit to the event. And you see here that to compute these sensitivities exactly, you need to store the state before the event happens. So this kind of increases your memory usage, but you really need this to compute your gradients exactly. And for implicit events, it's a very similar story. So you just store the event location, you store states and parameters. But in addition to this update rule, you get another update rule that depends on the condition function. And that's because for implicit events, when you change the parameters, also the time at which the event is triggered will change. So you kind of get two contributions to the equations that you need to update. And well, this is all implemented now in SciML sensitivity, and we have like some examples for some toy problems, for example, these cell population models, where we have a very simple ordinary differential equation here, and we say that we inject some cells in this population at a very defined time in the beginning. We can write down the code, and you see here, and in the end we will compute the sensitivity, so the derivative of this final state with respect to this parameter alpha. And yeah, so this is the forward evolution of this model, and we can check that this agrees with finite differences, forward mode ID, or also like discrete reverse mode applied on the solver operations. And one nice thing that landed this year is that we can also now use enzyme inside of these continuous adjoint methods, which highly improves like the performance. And just to show the second example very quickly, is like we can just change the condition for the event time to be something that depends on the state. So we need these extra correction terms. So the event is triggered here at, I don't know, 1.0, and still we can compute all gradients that we need to do, for example, some optimization. Yeah, this brings me to the end. So the gradient information is important for optimization tasks. And yeah, in the future, we want to do more robust differentiation of generic callback types. Thanks.
So our next talk is by Joshua on ML-based surrogate modeling of particle accelerators with Julia.
Okay, perfect. There we go. So, hi everybody. A bit of a change of topic here. I'm Josh. I'm a doctoral student here at MIT in physics. And today I'm going to be talking about a proof of concept that we did, which is using Julia to build machine learning powered surrogate models of particle accelerators. So before I get into kind of the physics and the context of this project, I want to give away the punchline. Basically, when we're designing these sorts of like particle accelerators and this machinery for this sort of thing, we have to run these very computationally heavy simulations that take a long time. And the idea is, can we build machine learning based replacements of that are good approximations for the sorts of things that we want to accomplish. These surrogate models are useful for a whole hearth of reasons, one of which being the optimization of the design of the kind of particle accelerator that you're building, and that's what I'm going to talk about today. And the surrogates and the flux packages were awesome for this. This is really an exploratory project to explore Julia as a language for me, so yeah. So for a bit of context, I'm going to talk about the experiment that I work on, which is called ISODAR. So I am a particle physicist, and my favorite kind of particle is called the neutrino. Neutrinos are very bizarre. They have a lot of behaviors that we don't really understand, as we do many of the other particles in the standard model. In fact, there's a lot of dissonance with neutrino experiments worldwide. They get numbers that don't match up, and a nice resolution to this sort of disagreement is the introduction of a new particle that hasn't been seen yet called the sterile neutrino. ISODAR is meant to sort of once and for all either rule out or rule in the existence of the sterile neutrino. And to do that, we had to have like a host of technical innovations that get us right to the sweet spot of finding the sterile neutrino. And one of those is the development of a kind of accelerator called an RFQ, which I'll talk about on the next slide. Here sort of you can see sort of schematically what's happening in ISODAR. This is being planned to be installed in an abandoned mine in South Korea. And I have resources at the end if you want to learn more about ISODAR. So the component that's necessary for ISODAR's design is called a radio frequency quadrupole. So hopefully a majority of us in the room have taken like Physics 101, and so we know that when we have an electromagnetic field and we put something that's charged in the electromagnetic field, you experience a force. And you can design these sorts of electromagnetic fields in a way so that you're like focusing a beam of charged particles, and you can like sort of accelerate those to the energy that you need to run whatever kind of experiment that you need. And that's sort of shown schematically, like in the bottom right figure. The little gray arrows are the electric fields inside the cavity of the RFQ, and then the green and the red arrows kind of show like the focusing and the defocusing effect that you see as your beam traverses the accelerator. A little more technically, we have a bunch of wiggles or like RFQ cells inside this RFQ, and that has the effect of like kind of alternatingly focusing in the X and the Y directions as your beam sort of propagates through your detector. Because of ISODAR's technical specifications, we run into a bunch of nonlinear effects, which make simulating and sort of like solving these differential equations as like the particles propagate through the accelerator very difficult. The biggest one being space charge. And that really blows up the like computational runtime of our simulations and kind of puts existing software packages to the limit. I think to generate the 200,000 samples that we used in this study, it took over a month on like the high fidelity simulations. And so the idea is that we want to replace that with like an approximator. So these surrogate models are useful for a variety of reasons. There are a couple that have been explored previously, one being uncertainty quantification. So you can approximate using these kinds of models the errors that you'll see in your experiment when you eventually get the thing up and running. You can use it as a real-time feedback tool. So when you're actually operating the machine, you can turn a knob and instantaneously see how the output or your beam quality is going to look. And then you can also use it in place as like an acquisition function for design optimization. And that's what we did, which is you can use this neural network in place of the higher fidelity simulations to run like a multi-objective optimization on all of the design tweaks that you can make to your RFQ. Great. So for this study, we had just north of 200,000 simulated samples. There were 14 what we call design variables, which are ways that we parameterize like the different features of an RFQ. And those are kind of listed by their like code names, I guess, in the bottom right. There were 6 objective variables or responses. These objective variables are very closely related to like the quality of the beam that you see on the other side of the accelerator. So like an example being transmission, which is exactly what you think it is like how much of your beam actually makes it through the accelerator. There were 2 objectives that in previous work was really hard to pin down, and that's objectives 5 and 6, which are called admittances. Admittance is like a figure of merit in my field for like beam quality. And the problem is that like we didn't have any way to resolve the asymmetries in the 2 transverse directions of the beam, the 2 X and Y directions. And so to do that, we extended our data set with one extra feature, which was really nice because we could link Julia to like a pre-existing Python script that like ran this thing for us. And that's how we got the number of RFQ cells or the number of wiggles as our 15th feature, which helped us a lot. We made some appropriate transforms on the data to make sure that we were showing our neural nets like physically feasible samples and that sort of thing. And then whichever neural net won from our hyperparameter scans was the one that we plugged into this design optimization at the end. And so here on these two tables on the right column, you sort of see the benchmarks for the percent errors from the best performing neural net from like a previous paper that we had done on this. And then RFQNet1 and RFQNet2 are the two neural nets that we had trained in this study. The only real difference between RFQNet1 and RFQNet2 is that we limited the data that we showed the neural net in the second case because when your beam transmission gets too low, it turns out that like your samples basically lose physicality, so they're like no longer physically realistic, and that tended to throw off the performance of the models. And RFQNet2 kind of blew it out of the water. The percent errors on that neural net are a third of what we were seeing previously, which is really exciting. And then the last thing that we did is we plugged in RFQNet2 into like the surrogates package, and we ran a multi-objective optimization on like sort of the technical specs of Isidar. Namely, you want your transmission to be as high as possible, you want your beam quality to be as high as possible, and you also want to match the energy that we need to like run our experiments. And you can sort of see the optimal design that we sort of converged on as like the orange star superimposed on like the rest of the Pareto front, which is blue. This like had like a pretty exceptionally low emittance, which is like really nice. It means our beam is really good quality, and a transmission of above 95%, which is also really awesome. So yeah, I mean, Julia was great for this. When you're careful about the data that you show these kinds of models, especially when it's like a physics problem, that really seemed to help things. And in the future, we'd like to explore more sophisticated neural network architectures to handle this sort of problem. So here are my references, and then if you want to learn more about Isidar, there's a YouTube video that someone in my group had posted that sort of runs through it. So thank you very much. It was like the radial basis. Yeah. Thank you.
Thank you. The next talk is by Avinash on accelerating model predictive control with machine learning.
All right. Hi, I'm Avinash Subramanian. I'm working on modeling, simulation, and control at Julia Hub, discussing accelerating MPC with machine learning, and particularly with emphasis on the JuliaSim suite of tools. So first of all, presenting an overview of the MPC suite in JuliaSim. So, so how MPC works, I think of it as having three separate pieces. So you would have like an optimization module over here. So what that does is it simulates the dynamic model forward in time and then calculates the optimal control actions that would give you closest to your reference or closest to any objective you desire. And then once you get these control actions from the optimizer, you would pass the first of these control actions into the system, which in this case is the actually deployed real-world system. And at the next time step, you would get a measurement from that real-world system, which in general you would not be able to measure all your states. So there would often be a third step, which is state estimation, which is some sort of Kalman filter or the nonlinear variance of this. So in the JuliaSim suite of tools, we are able to do a wide variety of this different configurations, so linear, nonlinear dynamics, linear or nonlinear observers, and also getting models from modeling toolkit, Julia FMUs. So in terms of speed and performance, and here the control inputs, like speed matters because the control inputs need to be available to the real-world system within a specific time frame. So we're able to solve like linear MPC problems at about 4,000 hertz, nonlinear MPC problems at about 1,000 hertz, and surrogatized at up to 1 million hertz. So the last is what I'd like to talk about. So in terms of a workflow, there are a few different pieces. So one would normally build a nonlinear model, say with modeling toolkit, and then if one wants to work on linearization, so linear MPC, there's this optional trim and linearization function, and then there is the open source low-level particle filters package that deals with state estimation, and then one would package all these different pieces up into an MPC problem in JuliaCon control, and if one requires further speed, that would involve MPC surrogates, which are trained with Flux and CUDA. So as a stylized example, so this would be a nonlinear research civil aircraft model, and why we chose this is because it has fast nonlinear dynamics, so like a sample time of like 0.02 seconds, and it's of intermediate complexity, so it's not really a toy problem. And the idea is you have 9 states, which are the forward velocity, sideways velocity, and vertical velocity, and then you have the rotational angles about these 9 states as other states, rotational angles and velocities. And you have 5 control inputs, which would be the rudder, aileron, tail, and the 2 kind of engine throttles. So again, the first step is usually symbolic modeling with modeling toolkit or JL, defining variables, equations as kind of expected. And just as, I'll try to make this larger. Or, yeah. So just as, yeah, quite straightforward, and also define equations. So this commonly comes from domain knowledge. And in this case, it is this kind of large mechanistic model that one would use over here. Following this, so in this case, MTK automatically gives the LaTeXified version of these equations, as one can see over here. Following this, one can perform the structural simplification in modeling toolkit, and then we kind of compress this large 123 system of equations to basically 9 equations with 9 equations and yeah, basically, and 9 reduced states, although they are somewhat nasty equations. So the next step, again, this is optional for linearization, is to use the trim functionality. So this basically gives you an equilibrium point or a point close to what you desire, which may not be an equilibrium point, if that's what's desired. And following this, one may linearize about its equilibrium point to get a state space model in delta coordinates. So then moving on to the state estimation piece, there are these functions that allow you to define in low-level particle filters various kinds of linear, nonlinear state observers, so one passing the dynamics and measurement functions from the real model, and then one would also pass in this case, Gaussian noise model, so the covariance matrices for the process and measurement noise. Then lastly, one would package everything into an MPC problem, and then there are various types that are offered. So it could be a linear MPC, quadratic MPC. It could also be like arbitrary functions, so economic MPC and robust MPC and so on, all of which are fully featured. So particular to this talk, the idea is to kind of get a sense of the philosophy of surrogатization with this MPC surrogates to JL package. So we have so far primarily looked at the standard MPC, and this here the control law is defined implicitly through the optimization. But the idea here is if this is the optimizer, it's basically one way of looking at it. If we want to just surrogatize the optimizer, is it's a static mapping from the state estimate and the reference to the control law. So one can get like an explicit so one way of doing surrogатization is to get an explicit control law, to train a neural network to get this explicit control law. So that's this sort of middle approach, which we think is sort of more suitable for this case. And alternatively, one may want to just surrogatize everything, which is both the optimizer and the state estimator. And There's some advantages and disadvantages to this. In that case, it will be a dynamic surrogate. So looking at the middle case as what I think would be most useful. So MPC surrogates provides basically a set of tools that where one would pass in the MPC problem and get out a trained surrogate of the control law. So, and then this can be, so they're good defaults, but these can be kind of, these can be configured. So since it would be like, in the middle case, it would be a vanilla neural network, so would have a depth width, and you can set these parameters and training parameters, and then call this get surrogatized function, and it would return a trained neural network surrogate. So if, just to quickly show the procedure of the above steps, so we could have linear MPC, nonlinear MPC, and so on, and nonlinear MPC with disturbance, and so on. So, and then one can get the surrogate model, surrogate of the MPC here, and then we can plot the results of the surrogate, the explicit surrogate law from the from MPC surrogates versus the implicit one through the optimizer. And we basically see, even for a fairly intermediate complexity example, we are able to get line-over-line performance here. And this is in a case where the disturbance has never been seen by the circuit before. So, and in terms of speed, it is in the order of, so this is in the order of 22,000 hertz, where the optimizer is in the order of 3,000 hertz. And then, so the target is to get between 10 and 100 times faster. So MPC surrogates overloads this common solve functionality. So one would pass in this MPC problem and this surrogate controller, and then this can be used to simulate with the explicit controller. All right, thank you. Yeah.
For public use?
Yeah, I can put it up.
Thank you. The next talk is by Julian on machine learning phase transitions, a probabilistic framework.
Hi again. So this talk, I'm going to present you a probabilistic framework for mapping out phase diagrams of physical system in an automated fashion from data. So phase transitions are really ubiquitous. In our everyday lives, we typically encounter them as changes between the three main phases of matter, solid, liquid, gas, as a function of external conditions such as temperature and pressure. And within a given phase, physical properties are largely constant. And so to characterize the properties of a given physical system really boils down to mapping out its phase diagram, and that's why we care about it. Now, more generally speaking, phase transitions occur when a system undergoes a qualitative change of its state as a function of a control or tuning parameter. And so that's what makes this phenomenon really universal, and phase transitions occur in many different flavors in many different domains. So notable examples are, for example, transitions within the conductive properties of cuprates, which are materials which show superconductivity at very high temperatures, or phase transitions in the entanglement properties of quantum circuits, in the collective motion of active matter, such as a flock of birds, or the behavior of artificial neural networks. Now, mapping out a phase diagram of a physical system is typically a hard task, and that's because the system state lives in a very high-dimensional space and is probabilistic. So for a given value of our tuning parameter or control parameter, we can find the system in various different states. And the physicist's approach to this problem would be to find a small set of suitable low-dimensional quantities which capture the essence of each of the phases that are present. And these low-dimensional quantities are what are called order parameters. So even though, for example, water is a very complex system, we can capture the phase transition, for example, from liquid to gas by simply looking at the density as a function of temperature, and we see that it shows a discontinuity at the critical temperature. So in this case, the density serves as our order parameter, and by computing, for example, derivative, we can immediately read off this critical temperature. Now, we would like to replace the physicist in this process, and the approach which results from that would be generic, so it would not depend on the details of the system, and that would really allow us to map out phase diagrams automatically from readily accessible data, be it from numerical simulations or experiments. And because it does not depend on prior theoretical knowledge, it could in principle enable the discovery of new phases of matter and could be used to identify unexplored phase transitions. Now, neural networks have had tremendous success in tasks such as image classification or other related tasks, and that's why those are sort of the main drivers of this development. So many of the machine learning methods for detecting phase transitions which we know of today are based on solving classification or regression tasks using neural networks, and all of these methods follow a similar workflow which is depicted here. So on the left is our physical system, and let's for the moment just assume that it's characterized by a single tuning parameter p, and we perform measurements of our system at various discrete values of this tuning parameter. That is, we draw samples x from the probability distributions, capital P, underlying the physical system. And based on this data set, we're going to train a neural network to minimize a given loss function. And once we have done this training, we're going to analyze its predictions y hat, and we're going to compute a scalar indicator of phase transitions I at each sampled value of this tuning parameter. And ideally, this indicator will then peak at the critical value and thus highlight the phase transition. Now, different methods differ in the choice of loss function, so the underlying classification or regression task we trained the neural network to solve, as well as how to compute the indicator based on these predictions. These methods can also be extended to physical systems featuring multiple tuning parameters, so in this case 2. In that case, the output of the neural network is typically multidimensional, and we are really looking for local maxima in the indicator map, which is here shown in black, that should highlight phase boundaries. Now, I've told you that many of the popular machine learning methods for detecting phase transitions are based on solving classification tasks or regression tasks explicitly by training neural networks. Now, this approach is really suitable if we don't have access to the probability distributions underlying our measurements. But it turns out that oftentimes we do have such access, and we can do better if we exploit this knowledge. So let's see how this can be done. So what we do is we replace the neural network by analytical expressions for the optimal predictions, y hat opt, which minimize the loss function. And these predictions are optimal in the sense that there's no other predictive model that would perform better on the task specified by the loss function. So how do these optimal predictions look like? So the optimal prediction for a given sample x looks as follows, where k denotes or indexes the set of sampled values in our tuning parameter space, and y sub k are tuning parameter dependent labels that differ from method to method. So to construct the optimal prediction for a given sample x, we weight each of these tuning parameter dependent labels by the corresponding conditional probability. And this conditional probability can be constructed by the probability distributions underlying the measurements across our parameter space, p sub k of x. Now, once we have obtained these optimal predictions, we can compute an optimal indicator of phase transitions by processing these optimal predictions in the same fashion as we did for neural network-based ones. And notice that the computation of these optimal predictions really boils down to knowing the probability distributions underlying the measurements, these p sub k of x terms. Now, in physics, sometimes we even have analytical expressions for these quantities or exact numerical values, and then we can use them. But more generally, we can work with any probabilistic description of our system in terms of generative models with explicit tractable densities. So what are those? Those are, for example, autoregressive networks, normalizing flows, or tensor networks. And we could also train or tune these generative models based on drawn samples. So let's see sort of a natural case where we have access to such a probabilistic description. We can speed up this process, and that's the task of mapping out quantum ground state phase diagrams. So we want to map out the phase diagram of the ground state of a 1D chain of qubits, which is described by the following Hamiltonian. So it contains a three-body interaction, coupling to an external field, and a nearest neighbor coupling. And so the two tuning parameters we consider is the strength of this external field H and the strength of this nearest neighbor coupling J. And we can obtain a probabilistic representation of the ground state of the system in the form of matrix product states via itensor.jl, based on which we perform a tomographically complete set of measurements. And then because we have access to the probability distributions underlying these measurements, we can very easily compute the optimal indicator over the sampled parameter space of any machine learning methods we desire. And in this case, this optimal indicator correctly reveals the phase diagram. So the optimal indicator peaks at these two phase boundaries and thus separates the three distinct phases that are known to be present in this model. So in conclusion, I've presented you a framework for mapping out phase diagrams in an automated fashion from data. And this framework is generic, so it doesn't rely on any specifics of the underlying system. And so that's why it's very well suited to be used as a tool to discover new phases of matter. And now computationally or numerically, it all boils down to the computation of these indicator functions, and we can approach this computation in two very distinct ways, in a model-free way and a model-based way. And as an outlook, we are currently applying these methods to systems outside of the realm of physics, and if you have any particular example, please let us know. And we're also looking to make these tools more easily accessible to the Julia community. Thanks.
So our last talk for the morning session, it's by Connor. It's on temporal network analysis with Julia, SciML, and dot product graphs. Sorry.
Hi, I'm Connor, and I'll be talking about a framework for modeling temporal networks using scientific machine learning. This was done in conjunction with the University of, that should be Canterbury, and with the thanks to Buffalo and LC for transport funding. So the problem that we're trying to solve is that we have a series of observations of networks, and we want to predict the next one in the sequence. So these type of network problems pop up a lot in, for example, protein interactions, network ecology, social networks, as well as symptom interactions. And so we may want to model these with differential equations. That means that we can get samples at differing time steps, and we can also generate predictions at differing time steps. And so it would be really nice, because it's difficult to model these discrete changes going from one edge to no edge at a single step. It'd be nice to have these in a continuous system that we can model that and then throw it back into an approximation of our network. Luckily, there is a way of doing this. We can use a singular value decomposition, which is a way of breaking down a matrix. So we go from our adjacency matrix to a continuous state by using the eigenvectors. Once we have these E, the series of E's are in a continuous latent space, and we can use scientific machine learning to model their movement. From there, we can take a symbolic regression to find a kind of more robust predictor ahead of time. We've found that just using the neural networks from SciML doesn't seem to work very well. And then we construct a random dot product graph, which essentially says that the entries of the random dot product graph are the probabilities that there are an edge between two given nodes in our adjacency matrix. So we'll go into each of these in a little bit more depth. For our singular value decomposition, essentially what we do is we take our adjacency matrix, we can find a kind of arbitrary number of eigenvalues of that matrix or associated with that matrix. You'll see a little bit more in a second. And then in our case, we take 2. And from here, we can see that this row here, for example, is associated with this point here. And so if we were to take 3 singular values, 3 eigenvalues, we would be embedding in 3 dimensions and so on and so on. So one nice property that we get from a lot of these networks is that they are very kind of, they need very few eigenvalues to describe the system. So just some work on singular value decomposition. We get 2 matrices generally that we want to model, which is L and R. And these are associated with the eigenvectors of A transposed and A transposed A. So this means that we can work on non-square matrices. So if we have bipartite networks, for example, we can still use this system for them. Here we basically just truncate them. So we could take all of the eigenvalues and would get a very good estimate of our network. But if we just take the first few, we can still get quite a good approximation of the system. So notably, these embeddings aren't unique. They can be orthogonal rotations of each other. And so to model them from one time step to the next, we really want to make sure that they're aligned as well as possible. And so for this, and as well as working with dot product graphs, we've created this package, dotproductgraphs.jl. Still working on that one, so if anyone's keen to help out or look more into that, feel free to contact us. And then for more information on singular value decomposition is this reference here. To give a little bit of an interpretation of movement in this latent space, here are the associated embeddings with each of our networks. And we'll be focusing on these 4 nodes here just to get an idea of how things will move. So at the first time step, we go from here to here. And as things get closer together, which is to say that they have more neighbors in common, they move towards each other in the latent space. So if we look at these ones here, we see that nodes 2 and 3 actually move on top of each other from one time step to the next. And that's because they have the exact same neighbors. So they're, in a sense, interchangeable within the network. Going from 2 to 3, we also have nodes 1 and 4 moving on top of each other here, because again, they're essentially interchangeable in the network from that point. I'll skim pretty quickly over this slide just because I think most people are familiar with scientific machine learning, but essentially what we're trying to do is combine some amount of domain knowledge with a neural network to create a differential equation. For this, for our proof of concept that we look at, we're focusing largely just on the neural network. Currently, we haven't actually applied it to any domains, but we wanted to know just how the neural network would perform by itself. For symbolic regression, we use symbolicregression.jl. We found that really helps to give a better prediction when predicting outside of the data, as you'll see in a little bit. And the idea is basically we can take our neural network, which we don't really have a good interpretation of, and we can move it into some set of known functions that we can interpret and understand a bit better. So the first system that we look at is this system here with 3 communities. So essentially we have 3 large clusters, and we focus on modeling just one node to kind of keep the problem size as small as possible. At each time step in this system, the edge with the, this node here is the one that we try and model, and it loses an edge with the community that has the fewest nodes in common with. So at the first time step, it'll lose this one here. At the second time step, it'll lose this one here, and at the third, it'll lose this one. Just a note, this is just a simplified representation. In the actual system, we're working with, I think, kind of tens of nodes for each of these bigger communities and many more edges just to generate a bit more data. When we run this whole process through for this system, we get this little animation here. So the green is the target node, which is where the node should be. The blue is the neural network prediction, and the orange is the symbolic regression prediction. So we see that when we're working outside of the trained data, so this is an ODE from starting from unknown data, the symbolic regression prediction works a lot better than the neural network. The neural network kind of very quickly veers away, whereas the symbolic regression moves a bit closer in the right direction. We haven't done any benchmarking because there's still a lot of optimization. We haven't looked at kind of optimum structures. This is really, really small-scale proof of concept. The other system that I wanted to focus on is this long-tail system. So in this, we wanted to look at this because the singular value decomposition really struggles to capture these kind of long-tail structures. You need essentially the same number of singular values as there are nodes in this tail. So we wanted to see what happens there. In the system, all that happens is this target node moves one further down the chain at each time step. Again, this is a small representation. The system that we trained on is a lot bigger. And as we see, this here is the target node kind of jumping all over the place. But it really is not captured by either the symbolic regression or the neural network prediction at all. So there's still a fair bit of work to do to kind of optimize this type of stuff. And we hope that this kind of gives a little bit of an idea of what future work could be. In particular, we really want to focus on GPU compatibility. We want to increase the ability for people to choose their own eigenvector engines, as well as optimize neural network structures for predicting these type of systems, and start looking at applications where this could be used. Yeah. Thank you very much. We wanted to be able to model continuously just because it meant that, for example, if you're looking at ecological networks, it might not always be feasible to sample at a regular time interval. And so being able to do this, you can kind of more easily model it or get samples and predict at different time intervals. Yeah.
Thank you. That's the end of the morning session.
So the yes, this is pretty much an equation of this is like the business method that
Are you here?
Perfect. Yeah. No, but this, no, please. This is going to be it's going to be useful. Good. Excellent. Nice talking. Yeah, let's do this. I can reach out to you. Nice.
So I'm sorry I was too long, but I skipped through the slides.
on now, but you can just,
Okay.
that would be good. Yeah.
Okay.
And if anyone asks you a question,
Yeah.
you could maybe repeat the question and
Yeah.
be like, the question was
Yeah.
this? And
Yeah.
that would be great.
Okay. Okay. A tutte e due. Ok. Cosa? Che ho mandato? Cosa? Se vuoi, tu ce l'hai? Credo che lo cercassero. Sì.
All right, so yeah, welcome everybody to the afternoon session. And our first talk will be about modeling world dynamics in Julia by Pierluigi Crescenzi.
Good afternoon to everybody. I'm Pierluigi, and today I'm going to talk about this Julia framework for modeling world dynamics, which we developed with all these people that you see in the slides and that I'm going to present during the presentation. So let me start with the motivation, the beginning of the history. Actually, while spending 1 week on the mountain with Emanuele, who is there, and who is a friend and colleague of mine, working on brain computation model, Emanuele told me about the problem of the fact that we live on a finite Earth, which means that we live on a world in which non-renewable resources are finite. And so he asked me, what can a computer scientist do? Actually, 6 years before, another friend of mine, a colleague of mine, Giorgio Gambosi, introduced me to Julia language. So if I'm not wrong, we are talking about version 0.4 or 5, something like this. And I immediately was fascinated by this language. I didn't know it before. And let me tell you that there are also some personal reasons, because my wife's name is Julia. And so I immediately say, okay, that's the language I should start working on. And so the two things combined, at the end, produced the package worlddynamics.jl. As I said, it's a Julia framework for modeling world dynamics and for simulating world dynamics. And in the world dynamics GitHub organization, actually now we have the package worlddynamics.jl, but we also have two other repositories, health4all.jl and vensim2mtk.jl, and I will say something about these other two repositories during the presentation. Okay, so what is the... If you look for the problem of modeling and simulating the dynamics of a world in which you have finite non-renewable resources, you immediately find references to what now are called integrated assessment modeling. In Wikipedia words, this is a term used for a type of scientific modeling that tries to link main features of society and economy with a biosphere and atmosphere into one modeling framework. So as you can imagine, this is quite an ambitious goal. And many people proposed several IAM. But in this talk and in the worlddynamics.jl package, we focus mostly on the family of IAM produced by the Club of Rome, which is a non-profit association. Some people talk differently about this association, but very active in the study of economy, world economy. In particular, this family started in '71 with a book by Jay Forrester. Maybe you know Jay Forrester because he was a computer scientist, quite famous. And he's also famous because he introduced what it's called system dynamics. And in this book, he proposed to use the system dynamics, which has been used in engineering, to study the dynamics of the world. And just 1 year later, a group of researchers, Forrester, moreover, was at MIT. And a group of researchers also coming from MIT, at least at the beginning, proposed an evolution of the model proposed by Forrester, which is called Word 3. I will say something more, but let me tell you that this tree model, along with all the variations that were proposed during the last 50 years, are included in the WordDynamics.jl package, mostly thanks to the work of Paolo, who also is here, and Isham, who is now has finished his PhD in Sophia Antipolis in France. Okay, Word 3, I don't know if you ever heard about the Word 3 model. It has been quite popular in a negative or in a positive way. It depends. But it has been very well studied for many, many years. And only recently, actually, in 2022, the Club of Rome proposed an update of this model. Actually, I wouldn't call it an update, a new model, which is called Earth for All. And this is described in another book which was published at the end of the last year. Earth for All is not included in the package of WordDynamics.jl, but it is included in the repository earthforall.jl. In this case, the main contribution has been by Aurora, who is also here, and Lucia, who is a postdoc at the Gran Sasso Science Institute. Okay, just to give you an idea of this, the increase of complexity of these models, this is the plot showing the number of variables and the number of parameters in each of these 4 models. So as you can see, we start from a very simple model, the one by Forrester, in which you have less than 50, actually 41 variables and 15 parameters. And then the last one, Earth for All, has more than 600 states and more or less 300 parameters. Okay? So this is the, what happened during the elaboration of the last model. Okay, why do we do this? Why actually do they? Why did they do this? Well, actually, when you, as far as I understood, when you develop an integrated assessment modeling, you do not really want to predict the exact values of the variables, but you are mostly interested in analyzing the trends, the main trends. So you don't want to forecast exactly the population in 2050, but you want to know whether the population will increase or will decrease. And most importantly, you want to analyze the effects on these trends by applying some specific policies. Now, this is what exactly the researchers of the Club of Rome did for all these models, starting from Forrester until up to the Earth for All model. And let me give you an example of this, actually a couple of examples. So, for instance, when you consider the Word 3 model, this is the forecast of the population variable if nothing changes. So the people in the researchers in 71 said, okay, if nothing will change in the near future, this is the trend of the population. As you can see, what happens here is that population reaches a peak more or less now, okay, in 2-3 years, and then it will start decreasing rapidly, okay? Why this? Well, okay, maybe there is also a very simple reason, because the non-renewable resources will decrease very fast. So this is the plot of the new non-renewable resources. And so since we will not have any resources, we will start to die as much as we give birth. And so actually faster then, and so we will decrease quite rapidly. By the way, I don't know if you already noticed it, but the logo of our package is inspired by this feature. You see, right? You see the population, and you see the resources going down. And this is an idea of Paolo. I have to say that it had this very nice idea of this logo with the colors more or less of Julia, but with the trends of population and non-renewable resources. From, yeah, this was 72. 72, yeah. That's a good question, actually, because the model was checked several times. And actually, all these verifications were quite positive, in the sense that the model not only was able to forecast the trends, but also it was not so far from the exact values. I think that the last one was in 2013, the last time they verified the forecast of the model. Okay, so the prediction is starting from 900. No, the start is in 900. 1900, sorry. 1900, right? Here. This is the start of the simulation. Yeah. This is because they used all the data available from 1900 to 1971 in order to, in some cases, estimate either the interpolation table or the equations that they proposed. Yeah, yeah. And okay, this actually this figure is the one that created the vast majority of critiques, because basically the message was, hey, watch out. If we don't do anything, we are going to collapse. And actually, this was also popularized as the collapse theory. So this is true. I mean, this image says we are going to collapse if we don't do anything. But in the book, they also propose several policies which would allow to avoid the collapse. And these people don't talk so much. Just to give you an example, here is the description of the changes that you have to do to the model. For instance, one is quite reasonable. For instance, the desired completed family size should be reduced to two children, starting from 75. Okay? Okay, in Italy, we are going towards this direction. I don't know in the other countries. But, and then other things, which means that you have to do some changes in the parameters. You have to change a little bit the equations. And the result, as you can see, the population now is stable. And the good news is that the non-renewable resources, yes, they decrease, of course, because we are going to use them, but not as fast as it was before. And the book contains many examples like this, many scenarios in which you can avoid the collapse. But this was not the message that the media transmitted to the other people. The message was, these people are saying that we are going to collapse. It's not exactly what they did. Instead, if you look at the Earth for All model, in the case of the Earth for All model, say the scenario in which you don't do anything, you don't change anything, once again you have the population which decreases, not so fast as before, but this time researchers were mostly interested to analyze what they call the well-being index, which is a combination of several economic and climatic and social variables, as you can see. And they say, watch out, if we continue like this, okay, the population will have this behavior, but the main point is that this index will decrease. And not only the inequality will increase, even if the GDP per person will increase. Okay? So the message here is, if we don't do anything, okay, the population will decrease at a certain point, and this is reasonable because we suffer of a problem of overpopulation. But at the same time, even if the GDP economically we are going to increase, the inequality will increase and the well-being will decrease. And then they say, and sincerely, I cannot be serious looking at this slide, if instead we do a giant leap, and you see this is really a giant leap, right? Eliminate global poverty, stop climate change, halt biodiversity decline, stop population growth, and reduce inequality. I mean, this is really a giant change, right? I don't know what you think about it, but sincerely, I'm not so optimistic about our future, okay? But anyway, if you do this and they formalize this by changing some variables and parameters, then things are going better. Still, the population will decrease, which is something that we want, because we want to be overpopulated, but the average well-being index will increase now. The inequality will decrease. Still, economically, we are going to increase. Okay? So this is why these people produced these models. Okay? And I think it was very interesting because to work on this, because actually this is something that makes us reflect at least on these problems in a way that it is more consistent with my way of thinking. I am a mathematician, so I like these kind of things. Anyway, so how did we implement this in Julia? Okay, this is, for instance, the World Tree model. You can see that there are 5 sectors, which are pollution, capital, non-renewable resources, population, and agriculture. Each subsector contains different modules, which are sets of systems of ordinary differential equations. And they are connected through variables. For instance, the variable pop here is used by the land development variable. Okay, so all these edges are labeled by the variable and say that this module depends, export this variable, and this variable is used by these other modules. Okay. So Earth for All actually didn't change so much this kind of organization, but the sectors now are many more, 12 actually. And so you have, for instance, the labor market sector, the public sector, the climate sector, the well-being sector, and so on. And still you have all these variables connecting the sector. I mean, when you look at this, I think that maybe if you know Modeling Toolkit, I think that you agree with me that Modeling Toolkit is the perfect tool to formalize these systems. Because we have models that you can compose into one bigger model, and then you create your world dynamics model. The only thing that we add with respect to Modeling Toolkit is a way of computing automatically the connection between the systems. So the variables which are used of one system which is used in another system, with the constraint that you have to use so far the same name, okay, for the variable. So now you don't need to specify all the connections between the systems. You just respect the constraint of having the same name, and our software will do automatically the connections. Okay, so how did we verify that our implementation was correct. Okay, in the case of Word 3, the code was in Dynamo language. I don't know how many of you have ever heard about Dynamo. It's an interesting system for simulating discrete systems, and developed exactly at the beginning of the 70s. There are still books in user manual of Dynamo, but of course Dynamo is not here anymore. Okay. So what we did, we translated all these Dynamo equations into Julia ordinary differential equations. Now the problem is that we had the book, but we had neither the code in a digital way. Okay, this was easier to have, and we did not have the simulation values. So how could we verify whether our implementation was correct? I have to say that there were already other implementations in Modelica, in Benzim, in Python, in Stella, but still, how did we know that these implementations were exactly the same model of the book? So we used a very nice way, I think, which is allowed by the power of Julia, which is just a position of images. And so we did something like this. This is you have the scanning of the image of the book and our plot. And then we just put one over the other. And I mean, sincerely, I was surprised to see how well the curves fit. And we did this for more or less 100 figures. And all of them were like this one, believe me, apart from a couple. We never understood why they are not exactly the same. But what else could we do? I don't think that we could do something different, because we are talking of something which was in the 70s. Okay, in the case of Earth for All, things are much better. Because in the case of Earth for All, the model was released with the code of Benzim. I don't know if you know Benzim, which is a simulation tool. Actually, it's a proprietary tool, but you can use a reduced version for academic research. And in this case, we had the code, and we had and so, since we had also the Benzim tool, we could also have the simulation values. So in this case, not only we did juxtaposition of images, but we also computed the error between our values and the values of the Benzim released model. And so, for instance, we have figures like this. This is the population. So you see the curves. These are the two scenarios I was talking before, the bad scenario and the optimistic scenario. And actually, there are 4 curves here, but they are so similar that you don't distinguish our curve from the Benzim curve. But we also computed the maximum relative error, which in this case was, as you can see, 0.0024 and 0.002, okay? Which means that we could be confident that, at least in the case of population, the simulation was correct, our implementation was correct. And we did this for all the variables, and I have to be honest, there are, I would say, 10 variables for which the MRE is bigger. And if you look at the curve, there are some differences, but sincerely, I don't know why. We have to discover the reason for this. Anyway, what are the advantages of this? Okay, first of all, modularity, but this is quite clear, especially for a computer scientist, this is a clear advantage. Moreover, you can imagine that if you don't like the climate model produced by the Club of Rome, you can remove it, you can put another climate model as far as you respect the API of the model, right? So this is clear. Then you have transparency. All code is open source. Our code is open source. Modeling toolkit is open source. Julia is open source. I mean, everything is open source. Instead, in the case of Vensim, even if the model is open source, you don't know exactly how some functions are implemented. So actually, there is still one function that we don't know how they implemented it. And the way they implemented it is different from the way Stella implemented it. And our implementation is equal to Stella, but it's slightly different from Vensim. So we don't know what's behind. In any case, we are also, with Mael, we are in developing a translator from Vensim code to worddynamics.jl so that we can do this with other models produced in the literature. Documentation. I think that this is, I'm a little bit proud about this because while for the Word 3 model, there was an entire book, very clear, really very clear. Every equation was explained and so on. In the case of Earth for All, you cannot find the description of the equations and apart from the code. So what we did, we say, okay, at least we can try to create automatically some documentation which says for any variable, from which are the use variables, which variable is using it, what is the initial values, and for instance, and then you have also the equation, okay? So this is a way of giving automatic documentation of the model, okay? Of course, you can, in the description of the variable, which is one feature of Model Toolkit, you can write whatever you want. But at least now you have this connection between all the variables. And then what else? I'm going to finish. Of course, we are going to use the firepower of Julia, okay? I mean, as I told you, I love Julia, the language, but also my wife. But, we can use all the power in scientific computing. For instance, now we are starting with Lucia, analyzing the sensitivity of the model. We are talking about 600 variables and 300 parameters. So it's a big task. Or we can do some graph mining. This is a very nice feature of Modeling Toolkit, which allows us to create the graph of dependencies, analyze this. I don't know if it is useful, but I mean, for me it's interesting. And finally, we can also use what Chris already talked at the beginning of this conference about the universal differential equations and the possibility of using machine learning techniques also for systems of ordinary differential equations. This is the references. As I told you, all the plots have been used by using our package, and I think I have finished. And if you have questions. I'm a little bit late.
Any questions?
Maybe I can repeat. Maybe I can repeat it.
Thank you very much for the very interesting talk. During validation, there were some deviations between your plots and the ones from the 70s. So did you use the very same numerical ODE solver with the very same settings as they used it in the 70s?
Okay, that's a good... yeah, sorry. So the question is, since I said that there are some discrepancies between the picture in the book and our simulation, the question is, did you check that you are using the same solver with the same parameter? It's a very good question, actually, because we don't know what.
Yeah, actually, maybe because maybe your results are even better because they use.
Actually, I believe it is so. I believe it is so. Moreover, Dynamo was not a solver of differential equation because it's like it was a discrete language in which already you have the solution. And we suppose that they just obtained by using the Euler method to write the discrete system. But we don't know what is, for instance, the step. We don't know it. So yeah, that's a very good question. In the case of Vensim, we could do it because in Vensim, they say, okay, you use this solver with the Euler solver with this step. We did exactly the same, and that's why the curve are exactly the same. Yeah, yeah. And this is also interesting because I didn't say that in the case of when I say scientific computing, I think it would be very interesting to analyze also the sensitivity of the system to different solvers and to different steps for the solver. Yeah, I think this is also something that should be explored. Yeah.
Thank you very much.
We might not have time for any more questions, but maybe offline you could ask. Yeah, so
okay.
Thank the speaker again. Yeah, so next we have Albert and Alan talking about magnetic navigation in Julia.
I'm putting that in just in case. Duplicate the screens. Duplicate the screens. You don't want to present it, do you? What's this? Great. Hi, everybody. I'm Albert Gannat. I'm a postdoc at MIT. I'm in the Julia lab. And
I'm Alan Walliver, technical staff member at MIT Lincoln Laboratory.
Great. And we're here today to talk about knowledge-informed learning in magnav.jl for magnetic navigation. And in general, we're going to introduce you to magnetic navigation if you haven't had any background in it. And so we're part of a larger team that works on this project. And it's a collaboration between the Air Force, MIT, and Lincoln Lab. So you can see me in the middle with MIT Julia Lab, and you can see Alan with Lincoln Lab on the right side.
Jonathan's in the audience.
Oh yeah, we have Jonathan as well from Lincoln Lab. He's one of the co-PIs on the Lincoln side. And just to introduce you a little bit to the actual problem. So what we're looking at is magnetic navigation. And so the general idea is that the aircraft is flying somewhere and the initial position is known from probably GPS, but then that signal is lost and you're not able to navigate anymore, but you still have an INS system on your aircraft, so you have an inertial solution to where you are. But that INS drifts over time, and so we can correct the INS using magnetic measurements, and you basically compare some measurements from the aircraft to some known magnetic anomaly map, and we're going to dive in a little bit more into these maps in the following slides, so don't worry about what that is right now. And just to introduce you to what we're specifically trying to solve with this problem, The signal that's actually measured isn't just the magnetic anomaly field, the thing we care about. It actually contains multiple components. The first one is the core field. That's what your compass would really measure. It's the very large scale signal. Then there's temporal variations, also known as space weather, and that's different smaller magnitude signals going on in the ionosphere. Then there's the anomaly field, and that's what we care about. That's basically the crustal field of the Earth, like the rock bed, that type of thing. Then there's one other signal in your measurement, and that's your platform effects. Basically, the aircraft has its own signal, and it's treated as noise. And for different aircraft, that noise is a different magnitude. So for a geosurvey aircraft, we'll see an image of that in a following slide. They basically measure out the back of the aircraft on a boom, and it has very low noise because you're so far away from all of the different equipment. But on a fighter jet, it's a little bit different. You can't really put a boom on a fighter jet, and so you have to try to measure somewhere in the aircraft, and there's extremely high noise. And so that's the problem we're really trying to solve eventually. And just to give you an idea of the kind of overall steps for doing this type of navigation, there's some sort of sensors, the INS system, like I mentioned before, magnetometers that measures your magnetic field, and you have other sensors as well, barometer, that type of thing. You get these different readings, and you need to compensate the magnetic signal. That's the real challenge, to remove these platform effects, we call it, or the noise in the magnetic signal. And those signals go into the navigation algorithm along with some magnetic anomaly map. And the state-of-the-art model is a linear model that uses basically two different magnetometers, a scalar measurement and a vector measurement. And then there's this linear correction term. We're not going to worry too much about these coefficients. They're Toles-Lawson coefficients that are found using a special calibration maneuver that's done ahead of time. But long story short, it's a very simple linear model that's been used since the 1950s, and more or less we're trying to improve on that. And so just to kind of summarize the problem here, this is a geosurvey aircraft. This is how the measurements are currently done by geosurvey companies, and they measure out the back using a tail stinger, they call it, or it's basically a boom. That type of system is not realistic in operation. And so what we want to do is measure somewhere in the aircraft with these temporally corrupted measurements. And so we're doing all this work in a package called magnav.jl, and this is open source. We'll dive into a little bit more in the following slides. But at a high level, it has basically 4 different type of areas. The first thing is you can load in or simulate different magnetic data or INS data, and there's a bunch of open source data that automatically is downloaded with artifacts. And then there's also a bunch of map functions, a ton of map functionality to generate that map like we saw before, and we're going to actually demo that later on. And then there's different compensation models, which are used to clean up that magnetic signal. And then finally, there's different navigation algorithms. And just a few months ago, we released version 1.0, so the code's pretty stable now. We're actually on version 1.1 as of a couple days ago, and it's not currently registered, but it should be, I think actually tomorrow. There's a 3-day waiting period we didn't know about. It was supposed to be registered for this talk, but very soon you can just do add magnav, and it'll just work. We have all the things you'd want for a package. We have a little API, and you can see our symbol in the upper left. I designed that. And then we have a Docker that you can use if you just want a quick start and not have to worry about installing all these different packages and whatnot. We also have a custom flight data set. Like I said, it automatically gets downloaded with the package via artifacts. So most people don't have their hands on any real data, and we have a very custom, nice data set that was generated for this project, this larger effort. And then more recently, in the past few months, we've added some new capabilities to the package that are designed to move towards using it in real life, using it in operation for like the Air Force or that type of thing. And so we added a navigation filter that has real-time capability, so you can take in one measurement at a time, figure out where you are, take the next measurement, et cetera. We also have 3D flight capability. For development, it's a lot easier to use a 2D map, but if you're out in the real world flying around, you're in 3D. And then finally, we have different functions for for combining maps and plotting maps and that type of stuff, and we're going to demo that later. It's kind of cool. And then Alan, oh, actually I have one more slide I forgot I added, just because it's relevant for the demo later on. So to generate these maps, it's kind of interesting. They fly around with that GeoSurvey aircraft, and they're on this thing called the drape. Basically, they're trying to go as close to the ground as reasonable. And then if you actually want to generate a map, you do this process called upward continuation. So if you want to map at this blue level, you just upward continue the map. You take all these values, you move them upward to the blue line. But if you want to map at a lower altitude, you do the upward continuation for a lot of the points, but in some cases you do downward continuation. And that's actually very unstable. The noise kind of expands, or it grows if you do this downward continuation, because it uses some Fourier transforms, that type of stuff. And so in general, you want to only do upward continuation. Yeah, I'm just giving a little background because we're going to show something related to this later on. All right, Alan.
And now onto the knowledge-informed part of the talk there. So what's interesting about this, the data set, the package is when you go get it, there's this sort of wonderful like machine learning problem that you can go try to tackle. And this is sort of a remix of one of Albert's earlier slides. But the thing to note here is we have this mathematical model that we sort of know and understand. Like the aircraft itself, we want to learn how to subtract that signal off. And so in the parlance of this field, they call that calibration to learn the effects of the aircraft and compensation to remove the confounders, which is really just training and inference. So you can just substitute that whenever you hear me say calibration is training, compensation is inference. So we have the permanent and the induced and the eddy fields. They're like vector components. If the plane flies over sort of a magnetic mountain, it'll induce like a larger field in the plane, and we can understand that just by looking at the map. Similarly with the eddy field, and the permanent field just rotates with the aircraft. And so we like this sort of explainability component, and we were thinking, how can we keep this in a sort of knowledge-informed pipeline with machine learning? And then we'll let the neural network take care of these transient fields, the communications, radar, lights, whatever else is going on in the cabin. And so we thought, we have this Toles-Lawson model. How can we inject that knowledge sort of like in the same way in 4 different like parts of the pipeline? And the one I'm going to talk about, the one that works best, is keeping it in the architecture itself. And because Julia has flux.params, it turns out you can put things outside of your normal like chain and just train on everything at once. So it's very convenient to try this. This is an example of that. So normally you have your neural network and whatever number of hidden layers you like down here. But up here, this is sort of an explicit representation of that Toles-Lawson mathematical model, where I can keep the meanings of the permanent, induced, and eddy fields and take a vector norm and subtract off a scalar correction. And so I wanted to test very quickly, does this actually help and how? So the way we did this is we have this existing data set. I selected 20 instances of one small line. So there are flights and flight lines, and every flight's made up of multiple lines. So 20 instances of one line, 20 instances of 2 line, all the way up to 20 instances of 25 lines. And I wanted to see like how quickly can I learn that field that I want to compensate with. And so here we're combining these 2 techniques at once. And then I'm going to test on 7 held out flight lines. And so what you see here is this is the result for those 200 sort of trained test runs. And each point here is some nanotesla compensation error. So over here, this is training duration in terms of flight time. And so what we want to do is get away with as little flight time as possible, because you have to fly the plane for 12 hours and then compensate. Well, you know, that's maybe not helpful for operations. And so the thing I want to draw your attention to is when you just use a regular neural network and you don't do the informed architecture, things after you add enough hours like sort of settle down. But the place that I was very interested in seeing is early on, if you use this knowledge-informed architecture, with just like less than an hour of data, it seems to hold together better. So when I'm adding to my mathematical model that I already know, then I don't have to use as much data. And I repeated that on several of those other held out flight lines. And it turns out, like, just to prove, like, I didn't just pick the one flight line where this worked on. Sometimes it doesn't help very much, but it doesn't hurt, and sometimes it helps kind of a lot. And so the operational relevance there is that we can calibrate in as little as 30 minutes of data collect, but this knowledge-informed architecture doesn't seem to help beyond a couple hours. The bonus is we get some explainability out of that. So on the left here, you can see in blue the uncompensated magnetometer, and in orange, the actual anomaly map that we were trying to get to so we can do our measurement. You'll notice there's some spikes in it, and if you look at the current for the strobe lights, there are spikes in that. So the lights are turning on and off. It's messing our magnetometer readings. And they exactly overlap there, except for a few spots. There are spikes that weren't on the current. So where do those come from? It turns out when the plane is banking, it's changing its alignment with the Earth's magnetic field. And that changes like the amount that you need to compensate. And so you can see as this plane's making a little turn, there's a spike. Some of that's accounted for by the Toles-Lawson model. But then there are other times that there are spikes in the neural network, and that's accounted for by those strobe lights and things. So we get this bonus in explainability. We need less data. And then in the end, it doesn't always hold up, but that last step, the navigation accuracy, can be better too. And then the thing that we're looking forward to like now is trying to bring some of that into the Kalman filter itself. And a thing Albert did for his dissertation is actually embed the weights of the neural network into the filter states themselves. And then, and you can do this with Toles-Lawson or both. And it turns out when you do that, this was actually from a real data collect we did later on. The two approaches that are working best are the online version and the informed version for the navigation error. And with that, we'll do some demo of the map.
Yeah. All right, so we've been working on creating some demos that we're going to put in the public repo. They're not actually up yet, but they will be very shortly with the next release. And just to give you a little bit of background on how these maps are generated, because they're important for the navigation. And so generally, you start with some sort of GXF file that's kind of a standard map file. And we have this built in magnav.jl that you can convert that to an H5 file, HDF5, for fast loading and unloading, or I guess saving of the map file. And so this is what the raw map looks like. And then before I mentioned the GeoSurvey aircraft, and so what they actually do is they literally just fly back and forth in these lines. These are flight paths for how they actually collect the data, and then this is compiled into a map by the GeoSurvey company. And then I'm not going to show some steps where we're importing some maps that I've already processed, but overlaid here are 3 different maps. Let's see if I can zoom in. 3 different maps are shown here. One is the NAMAD map. It's a large-scale map. And it's not the sun, don't be fooled. And this lower part down here, this is all real data. And what's going on here with these lines, this is all filled in using k-nearest neighbors. Basically, the map kind of ends right here. And so just to make the map complete, you have to fill it in. And that's important for doing that upward continuation that I mentioned before. If you have a bunch of zeros in your map using a Fourier transform, it's a big discontinuity and it's not going to perform very well. So you have to fill it in with some values. And then this greenish map here, this is the Eastern Ontario map up by Ottawa. And then this gray map is the one I just showed there. It's the smaller map. We're going to skip this just to give Alan more time. And for that upward continuation, so actually what it does in the function itself, it's kind of fancy. It actually expands the map outward because basically it's collecting, the upward continuation assumes an infinite map. And so what you want to do is expand the map. You don't actually have data, but you can kind of use fake data to help the magnitude of the value be more correct. And it does this fancy thing where it wraps each of the edges, so this side actually matches this side, and top matches the bottom. And it's all meant just to give the most accurate upward continuation. What's
the black line?
Oh, that's just the original map there, and so everything outside of it is filled in. Yeah. So this is the Eastern Ontario map. And now we have this functionality where we can actually combine maps. So I mentioned there was the NAMAD map over here and the Eastern Ontario map here. And so if you're flying around in this Eastern Ontario and suddenly you go over here, you don't want it to just have garbage for the map. So it'd be nice if they're combined and you can smoothly go between the two. And so this is a new functionality that we added to the package, and it's really meant so that you can do it in operation. And then I'm actually going to hand it over to Alan just to give him as much time as possible.
Yeah, we'll try to leave some time for questions too. So this is just an example walkthrough of one of these inform models. It's model 3 in the code if you wanted to look that up. But basically here I'm showing how you can select a flight 1006, which is composed of several lines, perform Toles-Lawson compensation using these lin-comp params, which are also defined in magnav.jl. This is an example of the field that we're looking for, and then the very noisy uncompensated vector and scalar fields there. So here I'm just selecting one of the little loops that Albert was talking about to do the calibration, and training that model. And here, I set myself the challenge of I want to use a single scalar magnetometer, a single vector magnetometer, and using the same flight, so lines 3 through 6, can I train my inform model using some features for the neural network, which are the currents, and the vector magnetometer and scalar magnetometer readings. And I'm just going to do 100 epochs here, set some fields, and the whole thing trains in like less than 4 seconds. And gives you these outputs. And so you can see how well we're doing here. This is similar to the chart I showed in the slides, but here we can dynamically update. And then also the navigation performance. And then there's a simple function you can call to create that GIF that I was showing you guys earlier, using some of that data. But yeah, the nice thing is we can come here and sort of dynamically change out things. And it'll just work. So if I wanted to add, let's say there's these discrete cosine matrices that sort of tell you how, like, which way the plane is banking. So this is just the diagonal of that matrix. And if I hit enter, then you can see it launches its training. We can see in just a second if it, so it gets less compensation error because I have more informative features, and it'll run through and you'll see it, it'll fit better. And yeah, I wanted to leave some time for questions too.
Yeah. And something Alan showed me, I didn't know this before.
Oh, yeah.
There's a nice little docs feature in Pluto, and we have pretty extensive docs for all of our functions and whatnot that explain everything that's going on. So yeah, if anybody's interested in trying out these examples, it should be pretty easy to kind of get your hands wet, hands dirty.
Cool. So yeah, we wanted to leave time for questions. Go ahead. I think he's got the mic, so.
Right. Yep, cool. Very neat. Do you think you can sort of reverse this and use your map to come up with a maneuver that would calibrate your model even more quickly?
So they do talk about you need to be able to exercise all the degrees of freedom for like the coefficients in Toles-Lawson. And I imagine as well for like if you have some of these cabin components, you need to be flipping things on and off, and you want to pick those up. But yeah, I think the main thing they try to do for that is make sure that they turn. So like the Toles-Lawson the calibration maneuver involves some like roll, pitch, and yaw, which apparently if you're on that flight is not enjoyable. Yeah. But you're right, like you could probably find regions of the map that would do a better or worse job of exercising those degrees of freedom.
Cool, thanks.
There's two over here, yeah.
Yeah. So you mentioned upward continuation. I was a little bit confused in the graph where you showed the longitude and latitude, and you were saying continuation, but it looked like your extending the map in the longitude and latitude. I thought continuation was about altitude.
It is, yeah. And so that's just, that's basically the pre-step for what you would do for upward continuation. So the first thing you do is you expand the map upward, or outward, and then you go upward, yeah. It's just, I'm showing a step along the way, basically.
So you imagine the field here depends on sources out here. And so it's easier to go this way and sort of bring everything in than it is to go down because you don't have extra information as you go down, which is why it's unstable. There's one more question in the back.
Hi, yeah, thanks. My old geophysics professor had always told me, or like basically in every lecture said, that the Earth's magnetic field actually changes with time. And so I was wondering, how much of a navigation error do you actually make if you assume it to be constant, as I figured you do here now, versus if you actually had like a live updating magnetic map? And whether this actually depends, let's say, on the region of the world. I don't know, is the Earth's magnetic field changing more quickly around the poles?
Yeah.
Or
So it does change over time. So if I could just go back to the slides here, these different components, the core field is slowly changing over time, and we account for that. There's a very well understood model, like a 13th order harmonic model that accounts for that, and that's super well understood. So that's not an issue. The temporal variations, that's a little bit more tricky if there's like a magnetic storm, that type of thing. Really what you want to do to account for that is you can just measure that on the ground or somewhere in space. You can have a measurement that accounts for that. And the anomaly field itself, what we actually care about, that's what all the maps are the anomaly field. That's pretty static. Like over a decade, it might change by like a nanotesla or two, like a very small magnitude. So it's not an issue.
So looking at the numbers here, you may end up with something like, I don't know, a meter off in your navigation in the end, because you're like several orders of magnitude, your temporal variations are smaller than the other ones. So is that kind of like the scale that we're talking about?
Can you repeat that?
Sorry, I'm just like looking at the numbers here of your nanoteslas.
Yeah.
And whether this basically means that if you assume your Earth magnetic field to be constant, that you end up with like your navigation being like a few meters off, which I guess
if you assume the core field was constant, you'd be way off.
Yes, exactly. But like your temporal variations, if they were constant, yeah. Okay.
Yeah, the temporal variations can also be accounted for with your navigation filter. You can add some states that account for that, so that's less of an issue.
Is it satellitetoolbox.jo that has the IGRF field?
Yeah.
So there's a Julia package that actually, there's this International Geographic Reference field, I might be getting this wrong, IGRF, that's updated every 5 years. It takes account the large variations that are slow over time. And then there are packages that will let you query latitude, longitude, altitude, time, and then you can pretty much account for that. It's a good operational question. There's one question here.
Are the reported errors in this work magnetic navigation only, or is that INS-fused magnetic navigation?
So the compensation errors are just nanotesla, like we know what the map should be using, say, a GPS signal as a reference, and then we know what we're measuring. So those, you could imagine, they're not really INS fused in that sense.
No, but I think for the navigation error, yeah, that's always with your INS. You would,
yes.
It'd be terrible if you just had your magnetic value. Yeah, you need to have some sort of idea with the INS where you are. And I actually made this plot while we were answering questions. So I changed the upward continuation altitude to 10,000 meters. Before it was at 395 meters. And you can see how the features kind of fade away as you go up in altitude. Basically, it's like a low-pass filter. So if you're up 10,000 meters away, you're not going to navigate as well just because you don't have as much signal up there.
So I'd assume you really have to fly like a plane through the magnetic field to do this mapping. I mean, like how much does a satellite sort of like sensors can give you sort of like a rough estimate that become a prior if you don't have, you have areas in which the airplane didn't fly. And can that work or?
No.
Yeah,
Short answer, no. So actually I had this little number pasted here, which is the distance to the ISS, so up in space. So if I run this, it's going to take a minute to run, I think. You'll see it's basically a point. You don't have any information at that altitude. For this field, you still get core field measurements, like that does change, so you can use that to navigate, but you're talking thousands of meters of error. But the magnetic anomaly field you just can't use at that altitude at all.
Okay.
Let's thank the speakers again. So next we'll have Domenico talking about finite element modeling of grids in Julia. Is the speaker here? So let's give them a couple minutes. Okay, so yeah, it doesn't seem like the speaker is here, so we'll just have a 30-minute break. You feel free to stay here if you want, or somewhere else. But yeah. Sorry? Okay. Yeah. Good to know.
pas? On pourrait.
All right, so yeah, I hope everyone enjoyed the break, and that's, excited for the next talk on solving optimal control problems in Julia. So,
Thank you. So it's a pleasure to be here, and let's talk about optimal control a bit this afternoon. So this is a joint work with several colleagues, including Olivier and Joseph, who are just here, Pierre Martinon also from INRIA, and some colleagues from INRIA Sofia in southeast France. So what this talk is about is essentially nonlinear optimal control. And nonlinear is important in this case since we really want to treat general optimal control problems. So just for the record, this kind of problem is, for instance, here you see a so-called Lagrange cost with a Meyer part, which depends on the initial and final value of the state, x at t0, the initial term, and then the final term, x of tf, plus some Lagrange cost, an integral cost, with some functional scalar, functional f0 here. And of course, you have some dynamical constraints given by some function f, which of course depends on x and u at any time between 0 and tf. So, and you might add some constraints clearly on the control values and on the state, plus clearly some initial and final constraints, typically an initial value, which is known for the state. Our core interests are more or less twofold. We work on numerical stuff, okay, so essentially methods, a long time ago in Fortran, C++, MATLAB, Python, and so. Now in Julia, we're a bit newcomers in the field. But anyway, we are very glad that Julia has so many things ready out of the box. And also, rather for the math side, geometrical in the sense of differential geometric tools. And it's very easy also to do this kind of thing in Julia, which is very nice since you can really mix symbolic and efficient numerical tools in the language. So that's what we really like about this. I will try to give a few hints. Where do we come from? Essentially, at the first step of this story, we would try to bridge two things. The so-called direct methods. For instance, we, with colleagues, developed BOCUP, which is a solver that essentially use, I would say, collocation scheme, right? And with a C++ code, AD built inside using CPP-AD and so on. And with this, we try to bridge this kind of computation with indirect method shooting, okay? Say multiple shooting. And in this case, you really want to do things in a Hamiltonian fashion. Because when you use the Montarguin maximum principle, for those who know what this is, which is the necessary condition for a control problem, you end up with a Hamiltonian differential equation that you want to solve. In this package, which was originally written in Fortran and MATLAB, there was a connection between shooting and path following methods, which is an efficient way to solve shooting. Okay, shooting generally is difficult because you do not know how to initialize it. Okay, so what you do, for instance, is you do path following, or what you can do is you bridge the two things. That is, you use first a direct code to have a rough initial guess, and then you switch to a shooting method. Okay, and this is more or less what I'm going to tell you about in this case. And this is what we did first using Python. Okay, we started this Julia stuff like 6 months ago, and you have still some material which is available online, application in a quite large variety of fields. So control is everywhere. That's quite clear. For instance, you will find here some notebooks in agronomics, biology, clearly standard examples. Godard, we'll come back on Godard. We had a nice example this morning by Eduardo with Interesso who talked of Godard. We are going to come back to Godard. That's Olivier that will let you know a bit about this. Shooting, homotopy. Homotopy is the same one as differential continuation in this case. Direct and indirect methods, also some application to Riemannian geometry, and so on. Space mechanics, that was a large trend for us since more than 20 years, I would say, and so on. So this was essentially done in Python, okay, to bridge this direct and indirect code. Now we are going to do this in Julia. So let me just give you the flavor of what we did. First of all, with a very basic example, okay? This is the very standard double integrator. Okay, you have a dynamics of order 2, a scalar control in the state, which is a two-dimensional state in this case, and you want to minimize quadratic cost, essentially the so-called energy cost, where you have this integral of the square of the control U. You fix some initial and terminal condition, okay, and the control is free, namely there are no control or state constraints in this case. So it's a very simple thing. You will get a smooth solution and everything. Okay, so what we do in just a few lines, this is the first version, sorry, the first version of the code of this description of this problem here. You just say that you define a model, okay, and in a very simple way, you will say that you have a time entry 0, 1, a state of dimension 2, one-dimensional control here, and you have some initial and final condition done, okay, and you solve. Of course, you precise the dynamics here, which is thus that x1 dot is x2 and x2 dot is u, and you have this cost, a Lagrange cost, okay, which means that you only have the integral part, and you solve and plot, okay. This is done using IPOpt. So thanks to our friends of AD-NLP models, we are able to use IPOpt in a quite efficient fashion in this case. You solve and plot, okay, and you get this solution where you clearly see that you reach the target that you wanted in terms of x1 and x2, okay. You reach 0 in both cases, right? The second way to do this, okay, is what we build using a very small DSL for our things. We wanted things to be as close as possible to the mathematics that you would write in this case. So what we just did is use a very nice package which is a ML style, okay, which allows you to write in a very simple way DSL. Okay, so in this case, what you want to say is that, okay, in the same way, we have a time, we have a state, we have a control, okay. You just here give the dimensions, initial and final value, some constraints here, very simple ones, okay. So it's x of 0, so it means that you have a boundary constraint at initial time, same at final time. Dynamics here, it's x dot, so it's a dynamics. You give it here, okay. You have a cost. Again, the same cost, the Lagrange one, and you solve, right? And again, you get the same plot, right? This was a basic example, just direct code, okay? Now, let me give the floor to my colleague that will tell you a bit more about a more difficult example, the Godard case, where you will see that we can use the direct code to initialize the indirect, the shooting code, okay?
So thank you, Jean-Baptiste. So in this example, we will combine direct and indirect method. Donc the Godard problem is well known, and the idea is to maximize the altitude of a rocket in a vertical ascent here. So you have here the objective function. And it's a problem with three state variables. So altitude, R, velocity, V, and you can see here all the forces, so the thrust, the drag, and the gravity. And you have the mass, and the dynamics of the mass is related to your thrust. So here we have normalized the control, so it's between 0 and 1, and we have a state constraint on the velocity. Okay, we do not want to, we have a maximal velocity. Okay. One more thing is that in this problem, the final time is free, as stated here. Okay, so it's an unknown of the problem. It's a decision variable. So first, we do the same things as before. We define the problem, and we will solve it by a direct method. So here you can see the parameters. Initial time is 0. Initial altitude is 1, so this means we start from the ground. It's the ground of the Earth. We start with 0 velocity, with normalized mass. Initial mass, it's normalized to 1. We have a maximal velocity, which is 0.1. And here you have the definition of the problem. So what is different compared to the basic example is that here since TF is free, you have to tell that TF is a variable. Okay, you have the time, the state, the control. You can label the components of the state or the control and use them to define the constraints like this. So you have here the initial constraint, the final constraint on the mass. You have the inequality constraint on the control between 0 and 1. This one, I don't really know if it's necessary to ensure that the altitude is more than the initial altitude, since we want to maximize the altitude. And we have the state constraints on the velocity here, okay, the dynamics, and the criterion, which here is a Meyer criterion and not a Lagrange one. So the dynamics is given with pure Julia code here. And you can note that the control appears linearly into the dynamics. And so we will have some singular arcs and some also constrained arcs into the solution. So now we can solve it by a direct method, huh? Okay, with a grid size, a small one, a small grid size, okay. So there are some few steps, and then you can plot the solution here, okay. So altitude from 1 to the final altitude. We can see the velocity here. We can already see that there is a constraint arc here, okay. This was the maximal velocity. You have on the left the state variable and on the right the co-state variable that will be useful to initialize the indirect method later. And here you have the control. With the control, we can see that there are 4 phases. A first phase with a bound control. The control is 1. A second phase with a singular control. A third phase, which we will see that is linked to the constraint arc. Okay, it will be a constraint. We can call it a constraint control. It's the control that makes you stay on the constraint. Okay, and then you have a off control, zero control. Okay. So this is the end of the direct method, and now we want to use this solution to initialize and solve it with an indirect method to get a more accurate solution, to get good, accurate solution about the switching times, so the switching times between these phases, okay? And you can notice also that, but this is quite classical in the direct method, that the control is oscillating, okay, on the singular arcs. But this is quite classical, and we will see that with the indirect method, we don't have this kind of phenomena. So to define the indirect method and the indirect shooting function, we need first to determine the structure of the solution, that is the sequence of arcs, so the bound and singular, constraint, and off arc. Here is just a plot of, I don't enter into the details of this, maybe I will see. Okay, see. Here, what do we do? We get the solution from the direct solution, so time, state, control, co-state. We define H1, which is the lift of the F1 was the control dynamics, okay? And H1 will be used to define what we call the switching function. And the switching function, when it's 0, it tells you that you are on a singular arc or here on a constraint arc. We define also here the constraint, the state constraint, okay? And we will plot everything to determine the structure. So on top, you have the control. In the middle, you have the switching function, and you can see that it is 0 on the singular part. And then on the constraint arc is visible here with the last plot of the state constraint, okay? So now we have the structure, and we can define the shooting function, which is more or less a concatenation of these four faces. But what is needed to define the shooting function? We want to integrate these four faces. So we need to have some function to compute the flow associated to this control, the flow associated to this control, singular control, the flow associated to the state constraint control, and the flow associated to the off control. So we have to define these four flows, and then we will be able to define the shooting function. To define these flows, we need, what do we need? We need the control laws in feedback form. We need 4 control laws in feedback form. So here we have some details, some mathematical details to compute the control laws in feedback form. I won't detail a lot this part, but what you can see is that US is the control law for it's a singular control in feedback form, and it is given by some computation of Poisson bracket of order 3, of length 3. Okay. I don't give you some details about that, not so much, but you have also here the control, the constraint control, okay, and you can see that it is given by some Lie derivatives of F0, which was the drift, and F1, which was the control field. And because you have a state constraint of here of order 1, but you have a state constraint, you have a multiplier associated to this constraint, and the multiplier also can be computed in feedback form, and here you have the expression. Okay, so this is the mathematical part, and this will help us to define everything with Julia, and this is done here. So it's quite similar, as you can see. H01, 001, H101 are simply Poisson brackets and are computed like this. So it's just a syntax to compute Poisson brackets. And you have the singular control, which is minus H001 over H101. Okay, so this is for the singular control. You have for the constraint control, and then you can define all the flows by command that you have in a method that you have in optimal control. And what you can see is that just with the OCP that we have defined before and a new information, which is a control in feedback form, we have a flow. So now we have everything to define the shooting function, which is barely the concatenation of these flows. So here is the shooting function. As you can see, here we have in the unknown of the shooting function the initial co-state and the 3 switching times and the final time. You can see that we just concatenate the flow. So we start with F1, it's when U is 1, Fs, Us, singular control, boundary control, 0 control, and then we just define the equation to solve. So here we have the constraint on the final mass. We have some transversality condition because the final altitude and the final velocity are free. Okay, we have some condition which tells you that you enter into a singular arc, and some condition which tells you that you are entering the state constraint arc. Okay, and at the end you have this condition which comes from the fact that TF is free. Okay, now what we have done, we have the structure, we have determined the structure, we have defined our shooting function. We have to find now a 0 of this shooting function, that's it. And to get a 0 of the shooting function, we will use a Newton solver. So it's quite sensitive to the initial guess. So we need a good initial guess, and this is the last part before the resolution. So here we have a simple trick. It's not very clever. It's just a simple thing to get a good initial guess from the direct method. T x, everything was given by the direct method. For instance, p0 is the p at time 0, okay? And to get the switching times, it's a simple thing. So we can see that we have everything. We can see that it's not very accurate since here you have the norm of the shooting function, which should be 0, or at least close to 0 at the end, but here it's not close to 0. So let's go to solve this, and let's see what happened. So to solve it, it's very simple. We use here minpack, but we could use another package to solve a nonlinear equation. So we simply solve it with minpack by calling fsolve on our shooting function with our initial guess. Okay, and then we have everything: the co-state, the switching times, and the final time. And now the shooting function, the norm of the shooting function is quite reduced. So it converged. Okay. What we do at the end is just we plot the new solution and compare to the solution we got from the direct method. Okay. But the difference here, when we solved the problem with the direct method, we started with an optimal control problem and we had a solution of an optimal control problem. But with the indirect method, you have some unknowns which are co-state, times, and such like that. And you don't have an optimal control problem. And at the end, your solution is not the same. So we have to recover something analog to the optimal control solution. And to do so, it's quite simple. We just have to use the flow we have defined before and compute the solution thanks to the 4 flows we have defined before. To do this in just one line here, we have defined an operator with the with the multiply sign, which concatenates all the flows, and you tell when you have to switch between them. Then you call it. It's a classical flow. You get the solution, and you can plot it. And then you have the solution here. You have the indirect solution on the direct solution, and just take a look at the control. You can see that everything is more accurate. Okay, so this was the part, the combination of direct and indirect method, and I just sum up what we have presented here. As you have seen, we have a high-level modeling of optimal control problem. We have an abstract form and a functional form. We have an efficient solver since at the end it's solved by hyperop solver, and it's handling sparsity, automatic differentiation, and so on. And we have also implemented some examples where you have the problems and the solutions. And I'll just leave the floor to Jean-Baptiste for the end.
Thanks, Olivier. So the message is quite clear. Direct is good, indirect is good. When you put them both all together, is better. Okay. Just a few words about what we are going to do. You can see here a quick video where we use a REPL maker to make a REPL, in fact, to define in an abstract fashion our problem. So maybe we can see here, okay, line after line, that we enter the problem in this DSL form. This is a minimum time problem, double integrator again, but mean time, okay, and you just expect a solution to be bang bang one, okay, so a simple one. So using this REPL, you just enter line after line, okay, your problem in abstract form. Again, when you see this QT, means that for every time t, okay, that you have this constraint on the state, and so on, and this is the result where you clearly see this bang bang form here. All this, okay, is on the website, so you can have a look at it. Just to conclude, what we are going to do is to add more solvers, that direct shooting, for instance, collocation, etc. Path following, of course, and we are open to contributions and, in fact, ideas, of course. There are already some problems online, so you can have a look this list of problems, quite a lot of them, with different features. For instance, you can see here the double integrator, which is a bit more complicated than the simple one, because you have this L1 norm of the control here. Okay, so you expect this kind of bang-bang solution here, bang +1, bang -1, or +4, -4, plus a singular part here, etc. Okay, so this is all available online, and you can use it for testing. The website is controltoolbox.org. Okay, so here you will find the documentation on the root package, which is optimal control.gl. Okay, and of course, let me give some credits to a lot of people, including people in the room, and in particular, we're very glad to use ADNLP by Tanguy, who just said a few words at 2 p.m. And of course, we heavily use MLSty to pass the small DSL that we made. Thanks for your attention.
Yeah, okay. Yeah, so first question is, you had this example that was showing the direct and indirect method. You showed that they compute about the same result, right? But the indirect method had a timing output from IP-opt. The direct method did not have a timing method with it. I was wondering if you had a comparison of the timings of anything on any problems there.
Yeah, well, actually, we did a comparison with a jump. Okay, if you hardcode the problem in jump, it's still quite faster. There's a ratio, I would say, 1 to 10, okay? But actually, Tanguy did a tremendous job more or less last week. And with now some sparse session stuff, it scales quite well. And I mean, in the end, it's all IP-opt solving. So it should be fine in both cases, I would say, right? But we didn't want to hardcode stuff. We really want to have a description as close to the math as is possible. So that's why.
But the direct method's not using IP-opt, right?
It is.
Oh, it is, okay.
It is, yeah.
Oh, it's just not showing the full printout there?
The?
Well, I was looking at the docs here.
No, yes, it's IP-opt, in fact, because in the case of ADNLP models, we switched to IP-opt as a solver, right?
Okay.
Yeah.
Yeah, because I thought it said it was using MinPack as a solver here.
No, that's for the shooting, okay? Because when you shoot, you look for a 0.
Yeah.
That's when you go for solve.
Yeah,
okay?
So I was wondering if you had a timing of that as well, because that's the only one in there that didn't have a timing in the printout.
Oh, the timing you mean for the shooting, right?
Yeah, yeah.
Yeah, that's absolutely fast. That's a question of seconds on a standard laptop.
Okay.
Yeah, why? Because you have the direct code and a very nice guess. When you start. Otherwise, you just get lost. Okay. You have 4 arcs, even in the Godard case. So it's a classic case, okay, but it's not that easy, in fact, because you have bang, singular, boundary arc, bang gain. So if you do not, in some way, capture the structure of the control at first, you'll be just lost.
Yeah, and then the other thing is, so you have this DSL here, but a lot of the DSLs that we have within the Julia ecosystem are built on top of Modeling Toolkit. I was wondering if, since there's a separate dynamics specification here, if they can interrupt well.
They can sure interact. That would be nice to do so. The difference is that we really wanted stuff just so close to the way we write mathematics, okay, including the differential geometric part. Yeah. So that's why. But of course, it would be nice to have a bridge between the two things. That's what clear.
Yeah. So yeah, I guess we could talk about building a bridge.
Yeah, sure. Yeah.
Hey, thank you so much.
Thanks.
So like kind of 2 related questions. One is in the direct method. Can you guys do general nonlinear constraints on the, on the states and everything?
That's the basic start that we wanted, full nonlinear stuff. Okay,
cool. And then, so I guess why then was in the problem you were doing some like switching methods to like enforce the constraints? The R max, I think it was, the R min. I'm kind of remembering.
Are you talking direct method or?
Yeah, in the direct method.
Yeah, okay. I mean, in the direct case, for instance, maybe I can go back here just to give you an idea. Okay. For instance, if you look at the Godard case, okay, what I can tell you probably is this. If you look at the GSL version of the problem, okay, there is only one difference, which is here. You see that everything, in fact, is linear. That's just a box thing. So this we do take into account because for IPOP it's nicer, right?
Yeah.
Suppose that you put some non-linear expression of U here, so we'll switch to non-linear stuff.
Okay.
Automatically.
Yeah, gotcha.
Yeah. That's the parser that does this.
Where was I seeing the G function? Was that in the shooting method
What
case then?
do you call G? Oh, G. Yes, G. I mean G. That was for the indirect for the shooting. Okay, because you want to compute. Yeah,
that was for the shooting. Okay.
Yeah, look. This one here, right? That's the constraint. You use it because you want to compute some Lie derivative to compute the boundary control.
Got it.
Yeah. Eduardo.
Hi, thank you for the talk.
Thanks.
I was wondering, so for the direct method, it seems pretty plug and play, so an export wouldn't be
that's the idea, yeah.
necessary. Could it be possible to automate part of the indirect method modeling part?
Well, that's more or less what we do here. See, for instance, you can label equation, okay? You have a label here, okay? For instance, for the final value of the mass, okay? You might have noticed that, for instance, m is equal to x3, so automatically you have aliases. You could put x bracket 3, okay? But you have this aliases for the state components here. And you see that you have this label one here. For instance, when you define the shooting function, you see here that we refer to this equation, meaning that here, okay, constraint, you call from OCP the constraint number 1, okay, to retrieve, in fact, the value of the mass. So there's an interplay between, of course, the definition and the stuff that you use for the indirect code, sure. And again, when you compute the flow here, it's straight away from the OCP, okay? So you will use, again, the dynamics here to build the flow, okay? Yeah, sure.
So yeah, I guess we can take further questions offline, but let's thank the speaker again.
Thank you.
Sorry, connecting.
I just connected this.
I think you might. So, like, is that? Yeah.
Oh, maybe I need to use this.
Yeah. All right, so for our next speaker, we're going to be hearing about quantitative systems pharmacology modeling using open source Julia solvers. So.
Thank you. Thank you everyone for being here at 4 p.m. on the last day of the conference. So you guys rock. My name is Ahmed Al-Muqaddam and I'm a senior scientist at Metrum Research Group. And just one thing to get out of the way before we start, for my son and wife watching online. Hi. So I just made their day. All right, so let's start then. So open science, immuno-oncology, QSP modeling using open source Julia solvers. So the work I'm going to be discussing today is actually a group effort. All these people are involved. These are people from my group at Metrum Research Group, the Translational Systems Pharmacology Group. So let's go back to the title here and do some definitions. QSP, Quantitative Systems Pharmacology, what is that? Well, it's the study of the quantification of what the drug does on the body, like the effect of the drug on the body in a mechanistic way, right? So if you give a subject a drug, hopefully it does something, right? Hopefully it does something. So the mechanistic representation quantification of what it does, this is systems pharmacology, in addition to the dynamics of how the drug is transported or distributed in the body, okay? So immuno-oncology, so oncology, cancer, so we want to treat cancer, right? So when people started looking at a system that is efficient in picking its target and eliminating the target, right? They found that this biological system already exists, which is the immune system, which is very efficient, right? Most of the time, okay? So this is learning by example. So can we use components of the immune system to help treat cancer, right? So this is immuno-oncology, right? In a nutshell here. So this is just a representation of what we're going to be talking about. This is just to give you a taste of what these systems might look like. So I'll be going through, there's going to be a case study that I'm going to go through, like a specific example of how this immuno-oncology system can be applied. But the main focus will be like on the Julia. How did Julia help us here? How does it help us, and how does the Julia ecosystem help us build such models and simulate from these, okay? And hopefully also make a case for open science along the way. So who are we? We are quantitative scientists assisting small biotech and large pharmaceutical companies to develop medicines, right? This is our purpose. How do we do that? Well, we use modeling and simulation, right? So we build these models, statistical, mathematical models, and integrate the preclinical and clinical knowledge that we have about a certain therapeutic agent and disease, and to see how does this therapeutic agent affect the disease, right? Can we help in decision-making along the way using modeling and simulation? So something here that I really liked about Metrum even before joining is that Metrum is for open science. Like, we try to push, contribute open science as much as we can, okay? So if we have a tool, we develop some of these tools to use internally. If a tool will be helpful to the community, we try to push it. Like, we validate it and we push it to the community so that anyone can have access to it. Because we believe that this is how science develops, right? Without open source, without publications, there won't be any science, right? So we try to do that. And I try to make the distinction always between open source and open science. So we've seen a case in a previous talk about how this function that was open source, it was available, but really it wasn't reproducible, right? So open source is the first step in open science. It's just one component. It's the beginning of the work, right? So you have to have enough validation, enough documentation, a way for the knowledge to flow, right? An easy way for flow of knowledge. And we think that Julia is a pretty good tool to do that, okay? So why did we select Julia for our primary systems pharmacology production platform? So we come from our background. So all of our work used to be R, right? And now we're shifting to use Julia for all of the systems pharmacology group, for all of the work that we do in our group. So why did we do that? Well, we needed a fast, scalable, and reproducible platform that we can build our models in. It has to be efficient. It has to be capable of handling larger systems, right? It has to be smooth, like it has to handle stiff, non-stiff equations, right? Because most of the systems that we have are stiff. So there's also the capabilities within the SciML ecosystem that you can automatically switch between non-stiff and stiff, which is great because it also saves time. Multi-scale, spatial. So spatial can be an important component here. If you're looking at immuno-oncology, right? If you're looking at a tumor, like a biological system, is not two-dimensional. It's not one-dimensional, right? It's a 3D structure. It's a spatial structure. So including a spatial component to our system could be very helpful. Like we could benefit, and our predictions could benefit from that, which is something that you can do in Julia. Like, you can use modeling toolkit with a symbolic representation of a PDE, and you can integrate your work this way. Agent-based modeling. So a tumor microenvironment and tumor cells, they are not homogeneous, right? They are heterogeneous systems, right? Some would respond to a treatment, some wouldn't respond to a treatment, so there is some sort of probability there. Okay, so agent-based modeling could help us also there. Like if this is a question that we want to answer, right? So we can use this sort of thing in Julia. So Julia has a package agents.jl, which I think is great, and it helps a lot being able to mainstream the defining of an agent-based model. Bayesian models, so quantifying your uncertainty, right? This also could be a very important aspect of your analysis. You have a model, you're making predictions, but how certain are you about these predictions? How certain are you about some parameters in the model? Okay, so Bayesian inference, so we can easily also use the SciML ecosystem, ordinary diffie-Q or an ODE problem, and just plug it in Turing model function, right? It just works, okay? So the composability of the ecosystem is pretty remarkable. I would say something else, like you would look at this system here. So this is just an example of the immune response to a tumor, right? So this is the model. So you can see a lot of nodes and edges, right? So ideally, you would have information and data about all of these nodes and edges, right? But almost always the case that there's something missing in your knowledge, okay? And hence, UDE, universal differential equations. We heard a nice talk yesterday about applying universal differential equations in systems biology. Same thing applies here. Like if there is some part of the system that you're missing, that you just don't know, right? Maybe you can stick a neural network in there, learn the neural network. Maybe even you can do symbolic regression and learn what that missing term is. At least it's going to direct you towards what nodes are impacting this missing thing, right? So this is all pretty nice, and these are all nice things about Julia that we like, and that's why we integrated our systems pharmacology group to use Julia. We also, because we didn't want to ditch R totally, right? So you can also use R and do R coding within Julia. R call works pretty well, at least for us. Like it worked pretty well so far, okay? So, yeah, so we already have a lot of published stuff. So we tend, all of our publications, we have this associated GitHub repo with it. All the code is provided. And this is an example of a code that we have out there. We have this open source Julia production code for monoclonal antibody PBPK model. A PBPK is a physiologically based pharmacokinetic model. It monitors the distribution of antibodies in the body, okay? So we were able to translate some of the code that was published in this paper, and we translated it into R and Julia, okay? And we have this repository that you can see both of these codes out there, okay? So just case in point here. So if you look at both codes, they are doing the same exact thing, right? And we validated that. The R code is about 6,000 lines, so it's a huge model. The Julia code is about 800 lines. So that's a huge improvement, right? It's much better to write, and it's much more readable. And a case for open source here, we actually used this code, so the R version of it, right? So we used it during the pandemic. So during COVID, we collaborated with Eli Lilly, developing the first monoclonal antibody to go to clinical trials in the world. And it was crucial that this publication, so we had a great appreciation that this publication was open source. And it was very well documented, okay? So we were able to grab, and actually I don't want to say something wrong here, but I believe that they also shared some code in Berkeley Madonna, if I'm not mistaken, right? So don't quote me on that, but I believe that's true. So it was very straightforward for us to take this and to help in the decision making. We were running against time at that time, so it was a frenzy. And we were able to use that to help in candidate selection. We had multiple candidates, so we were able to help in candidate selection. And the first in human dose, we didn't have any other data. Like we wanted to say what would be the dose to give to a human to go to clinical trials. And we were able to do that within the matter of months, which was remarkable, right? And it was all possible because of that open science mentality, right? So we also have in the process developing open source immuno-oncology models. So this is coming out of the pipeline soon, right? So keep an eye for that on our GitHub repository. So the example that I'm going to be talking about is the ADC. What is ADC? It's antibody-drug conjugate, all right? What's antibody-drug conjugate? We said that the immune system is pretty good at picking its target, right? If you give a drug, like in chemotherapy, these drugs are pretty good at killing cells, right? These drugs are pretty good at killing the tumors, but they're also pretty good at killing all other cells. So the specificity is important here, okay? So what if we have this drug and associated with some linker onto an antibody that is designed to target an antigen on the tumor, okay? So that helps with the specificity, right? It also helps with the half-life, because antibodies have longer half-life, so the drug can remain there for a while, okay? So how does that work? So you have the antibody and some drug bound to it. An important factor in the creation of these molecules is DAR, which is the drug-antibody ratio. Usually it's 1:8, and there's a whole like branch of literature about how to design these things. So let's say that you have associated two drug molecules to this antibody, and then the antibody goes around, it finds the antigen on the tumor, and then binds to it, gets internalized. Now, two things could happen. The linker that binds the drug to the antibody could break within this endosome, or it can get recycled, right? Actually, a third thing could happen also. The endosome could mature or transfer to lysosome, where the antibody gets broken down and the drug is released, okay? So in both of these cases, the drug would be released. Then the drug would go to its site of action. Let's say the DNA. It goes to the DNA and messes with it, okay? But also this drug could diffuse out of the cell, okay? It could also diffuse out of the cell and gets diffused into a neighboring cell, okay? And this neighboring cell might not have this receptor, right? But the drug is a small molecule that diffuses. That's what they do, okay? This is called the bystander effect, okay? Which is something that could increase the efficacy of the drug. It could also potentially increase toxicity, right? So there is a balance here to strike. So these are the key mechanisms that I've already discussed here. The drug itself is referred to as the warhead or the payload, linker and antibody. So these are the components. So as a motivating example, we're going to talk through the ADC modeling. So this is work that has been published already also. So again, open science. And usually how the progression in drug development goes is that we have in vitro data, then goes into the in vivo animal studies, and then ultimately human clinical trials. Okay, this is how it usually goes. So this model would recreate or would characterize the in vivo data. But as an example, we just focus on the in vitro system. We're assuming that we have an in vitro system that we want to model. Okay, we want to characterize the in vitro data that we're seeing. So let's take a minute here to just go through the typical ecosystem, Julia ecosystem that we'd use. Differential equations, of course. Modeling toolkit, of course. So data frames meta. So data frames is an excellent package, right? But coming from an R background, we're used to the tidyverse, if you know about the tidyverse language. And data frames meta is pretty close to that. So I personally find data frames meta to be an awesome tool. CSV for the transfer of knowledge. Plots.jl, we use that mainly for basic plotting. And then for more complicated plotting, we use Mackie, which is great. Algebra of graphics is also pretty close to ggplot2, which is the plotting package in tidyverse. Component arrays is pretty awesome because it really makes it easier to define the parameters, to define the variables, and to be able to index by name. So that's a huge benefit, especially if you have larger systems that you can't really keep track. Optimization.jl, of course, with all the optimization tools that are available in there and Turing for the Bayesian inference, right? So this is what usually you would see if you open any script that we have, like the starting thing. So SciML, open source software, scientific machine learning. We are very fond of SciML ecosystem. You can see the sticker here. So Metrworks is our cloud computing system. So we already have ways to navigate through the Visual Studio Code as the favorable IDE for Julia on our cloud system. Additional resources, you can find the repository for PBPK modeling, a tutorial that we had to do PBPK using R. And this is the drug. This is the monoclonal antibody that we developed. Nobody asked us about the name. So bamlanivimab. Okay, so PBPK paper that's out there with the code that's associated. So this is the model. This is how the model looked like from that paper. So this is a scheme from that paper. And you would look here, this is the PK part of the model. The PK is the pharmacokinetics. This is how the drug itself, which is the ADC, would transfer between different compartments. Now this is a very simple model. If you were here for my talk yesterday, you've seen the PBPK model, all of the different organs there. This is a much simplified version, right? So this is just 2 compartments here. And you have a component for the ADC and a component for the payload, because the payload could dissociate. It will have its own PK properties, right? If you're also here for my talk yesterday, you also know that I'm fond of my cursor, zooming cursor, so I'll be using it a lot. Right? So just heads up. Then the drug gets diffused into the tumor microenvironment. Then we have here 2 different types of cells. Cells that express the receptor, that highly express the receptor, others that have low expression of the receptor. This is just the experimental conditions, and everything that I explained is happening inside. Okay? So if we're talking about in vitro, so this is in vivo, because this part here, the PK, happens in vivo, in the in vivo system, where the drug is ultimately cleared, right? If you're talking in vitro, then you won't have this component. It will only be this part. So, and that's what we see. So I'm not going to go into details. So this is a dissection of every part of the model. So this is the in vitro system. So you have the antibody binds to a receptor, can dissociate from the receptor, gets internalized, the endosome to lysozyme. You can have breaking of the linkage of the linker. In the endosome, you can have lysis of the antibody. In the lysosome, in either case, the drug gets released. This is a target plus cell that has the receptor, but the drug then diffuses out and can diffuse back in a neighboring cell that doesn't have the receptor, like the bystander effect. So yeah, I'm not going to go through these. These are just details about how the model is actually being built. So you can see the code. So that's not a problem. So let's skip right to the end. So yeah, now that you have this model, you can simulate all different sorts of things, right? So you can simulate, like, for example, target occupancy, how much of the drug is bound to the target of interest, right? As your PD measurement or pharmacodynamic measurement. Then you can scale this up. You can scale this up to the in vivo level. So what if you want to see what was going to happen in a xenograft mouse, for example, that has the tumor? Then you can model this and you can run simulations. You see that the tumor growing here without any intervention. If you give the drug at different doses, you can have different effects, right? Here's the same thing, and here was a conclusion out of the paper that if you give the doses in fractionation, like if you fraction the doses across some time, it will give you a better result than if you just give the dose at once. So just a heads up here, we are going to be at this conference, which is a pharmacometrics conference, American Conference of Pharmacometrics. That's coming in November. We have a workshop there, Open Science Immuno-Oncology. And we also have a couple of packages coming out in this open source package suite to Julia to facilitate QSP modeling and simulation. And credit goes to Tim Nab, who did the groundwork on this package. So this is just a taste of what this is going to look like. So we're going to be rolling it out, working our way towards the conference. And you can see that it's kind of pretty close to how you would define your stuff in SciML. But you have these convenience macros. So you can define an init block here where you have the parameter values. These are initial parameter values. So you can change the parameter values as you go. And the initial values for the variables. And these are the differential equations. Right, so this is how you would define your differential equations. So another package that is more specific. So you can see that this package can be more like general purpose because any ODE-based model you can easily work through here. And our main thinking about having this is that we wanted to recreate the features that we already have in another R package, which is MRG Solve, that we also created in Metrum by Kyle Barron. And we know it works. It has been there for a few years now, and we know it works, so we wanted to recreate that here. So yeah, that's it. Thank you so much. And please, this is my email if you want to get in contact. And yeah, I'll be happy to take any questions you have. Thank you. Was everything that clear?
Just a short and easy question. Just to get an impression of the complexity of your models, is how many states do you have? What are typical simulation times? What is the scale you're talking about?
Yeah, big, but on top of my head, I don't know how the number of ODEs.
Approximately.
Like you have, for example, this PBPK model, there's 6,000 lines in R.
Yeah, but not code lines, but states or simulation times.
A lot of states. So if you have, like, for example, 15 organs, you divide each of these organs into like 4 or 5 subcompartments. And there's also the blood compartments. I don't know the combinatorics on this. I have no idea. Yeah,
okay.
But yeah, parameter-wise, yeah, it's a lot. Yeah. So this can be huge. Also, another feature that we like in Modeling Toolkit is the composing. So composing different models. So that could be also very useful here because you can modularize your models. You can have a QSP model. You can have a PBPK model. Join them together with a linker, right? So that's also something Modeling Toolkit would do very, very easy to do. So yeah, I'll check the number of variables and I'll let you know.
Thanks.
No problem.
So, yeah, let's thank the speaker again.
Yeah. Thank you.
Thanks a lot. So we have like 3 minutes to start, I guess. So we start on time. What did I press for screen? Windows. Yeah, duplicate.
All right. So which keyboard? Yeah, you can actually yeah.
And then is something wrong.
Yeah, so that looks like the right keyboard.
Is the projector turned on? Like there's totally no screen, no light, or?
What have you got?
This is
bizarre because I've been testing it earlier. Oh God. Give me a second, maybe. I try to reboot the machine. Oh, this is something wrong. Yeah, it's something. Let me just. This is some kind of bad luck, but let me just.
Sorry. Yeah.
Because I think it used to work. You know how it is?
Yeah, I think it's using the right
I will just
table.
try to reboot just in case, but maybe something else.
And is your talk slides only, or
Yeah.
like, could we move it to another computer in the worst case?
It's slides only. I could, of course, upload. Okay, yes, just in case, maybe I will just upload in a minute if somebody has another computer. But let me just. Should be starting. Come on. Let's try it once again.
So,
Right?
could you do us a favor and maybe we could use your laptop? Or, okay, could you just give an email to send the slides to maybe? Or, so you could maybe email it to Ahmed and
Okay, let us do it. Sorry for this.
What sort of file is it, by the way? What sort of file is it?
PDF?
Yeah,
or PowerPoint, what do you prefer? I have PDF, I always do PDF. Okay, so what is the email? Yeah, the email?
And the I can type it maybe?
Yeah.
MED. Sorry, MED.
How does it not work?
All right,
Okay.
got it.
Okay, thanks a lot for your help. This is stressful.
You just try connecting your computer and that.
Yes, let's try to connect the other computer. Okay, thanks a lot for.
Yeah, sure thing. So did you send it?
Yes. Yes, you have it?
Yep.
Okay. Two minutes, so 20% of time passed. I will do it quick then. Thanks a lot. Okay, great. Now let's hope this laptop is going to work. It was working, right? Or?
Yeah.
Oh, okay, it works here. It's Control L. How do I press Control L here? It's Command L, I guess, for full screen.
Yeah.
Okay.
You get to use the Zoom.
Okay, so I need to do this.
You can go take 8 minutes with questions. So.
Yeah, 8 minutes with questions. So I assume maybe let's do questions afterwards or something. Somebody approaches me or whatever. Microphone. Okay, so we're going. This one? No. Okay.
Okay. So hello, everyone. There was some technical issue, so we start a few minutes later. So this will be shorter. So I'm going to talk about working spatial data in Julia. So the spatial data, I mean here the data at OpenStreetMap that is divided into several levels. OpenStreetMap is kind of Wikipedia for maps, so we have all this data about the world that is around us. The data is available via XML and PBF, and it's multi-layer structure. There are things like nodes that represent points, ways that represent lines, and relation. And each of these can be tagged. So for an example, this is the campus that we are currently here, and this is an XML representation, like you have, for example, some building, Cambridge, and number 33. Okay, so this is the data, and now this is the set of libraries I'm working on. So these are the libraries working for mapping data. And those libraries include OpenStreetMap X for processing of spatial data. So this library is mainly oriented onto the road system. So if I have a road system, a system of roads, it allows to extract roads as graphs. And these are particular graphs.gl graph. It supports routing, road classes, vehicle speeds, etc. So some basic information about routing. There is also a kind of overlap with the package geodesy.gl because it's also supporting some algebra, some spatial algebra processing the coordinates. Now the next package, a corresponding package, is for plotting. So if you have a map, you can plot it using plots.gl or pyplot. And now I'm working on another package which is work in progress and should be registered soon. This is a package OSM toolset, and this has tools for extractions of points of interest and for slicing of maps. So this is the ecosystem that is being developed. So this is how you use the packages in OpenStreetMap X, OpenStreetMap X plot a file. So this is the Boston area around us. And for example, here I'm calculating a route from the point A to the point B, and this is how you can plot it, and you are getting such a plot as you can see at the background. So this is part of the package. Now, the package I'm now working on is OSM toolset for extraction point of interest, and basically it works like this, that you define what type of points of interest you want to extract. So for example here, some sporting attractions, but this is just a small part of the table, so this could be restaurants, pubs, businesses, and so on, everything, all the world around us, at least in the United States or the Western and Europe, it's cataloged on OpenStreetMap data. And then we have like find point, so I take some small part of central Boston, and I'm finding all the places of interest from this setup. So this is what I'm finding. So I'm finding the information about the places. Now this is a plot. Here I'm using a leaflet via PyCall. So this is the data that has been extracted in the previous step. And here you seeing all the locations around our conference venue. Additionally, they have been divided into 8 classes with 8 colors, like parking spaces are blue, restaurants are red, and so on. So this is the spatial information. Now, the next thing around this library, there is something which is named walkability index. If I'm interested in any location on Earth, I'm interested how the place is walkable. Okay, so can I walk to the school? Can I walk to school? Can I go to kindergarten? Can I walk to shop? So this is somehow the standard of living in the city, how easy it's to walk. And I'm working on attractiveness index, and it works like this, that is building a special attractiveness index from the point of interest data. And this is the locations of mid-strata center, and it's building some aggregates on the base of the data. So this is querying an attractiveness index. So this is also the Python library. You can find this on my GitHub account also with this code in Jupyter Notebook if you want to experiment with that and if you want to extract such information. So here is an example of this index. So searching this index is very fast. It takes some roughly like 50 microseconds per query. So actually it's possible, for example, to take a granularity. So here's a granularity of 100 meters step by step and take the entire state or entire country and just point by point to calculate the walkability. So this is a restaurant walkability. So how many restaurants I have within some range. So there are some ways how to aggregate it. And you can see the intensity of color. So you can see, of course, all the restaurants here in Boston are in the downtown. So all those packages are available online. Also online, if you go into my GitHub account, which you can easily find by typing my name, you can find sample Jupyter notebooks. So thank you very much for this attention. Maybe I can even take one question if possible, then thank you. Anybody has a question?
Okay, thank you. The grid is showing like it's like it looks like a regular grid. So I'm seeing stuff over the Charles River. So I mean, like how does?
Yes.
Yeah.
That's a good question. So the question was about stuff over the river. So it's using Euclidean distance, and it should use the distance using the roads. So it's using here Euclidean, just a simple Euclidean distance. So that's why you see the color.
So yeah, we'll take any other questions offline. And yeah, thanks to the speaker again. All right, so our next short talk will be on graphical displays for understanding mixed models.
Great. Hi, so I'm Philip. I'm one of the maintainers in mixedmodels.jl, and so I, of course, have an interest in how we can visualize them. And so, of course, we can do things like traditional regression diagnostics. So we can do fitted versus observed. We can do fitted versus residual. You might notice that the data on this model are truncated, and you can see this nicely as this kind of sharp line. This is actually an important diagnostic. If you don't think your data are truncated and you have this type of line, you need to think again. And we can also do QQ plots. This is all implemented in Mixed Models Mach-E so that it's very easy to do. There's recipes. Now, if you're like me and my colleagues, you're screaming at this QQ plot because the aspect ratio is not 1, and so that's what you really want for QQ plots. But I was not going to bother getting that right for this because I want to focus on more interesting mixed models specific plots. So for example, we have what we call caterpillar plots. For those of you in the R tradition, these were often called dot plots in LME4 and its predecessor in LME. And these are the BLUPs, the best linear unbiased predictors, perhaps better known as conditional modes because it's not clear in what sense they're best or they're unbiased. And basically, they're distributions of the offsets for each level of the group. So for example, you see on the horizontal axis, you have a particular individual. So we have, for example, subject 36 here, and it's sorted by the second column. We can actually specify in Mixed Models Mach-E what column you want to sort it by. And you can kind of see whether or not there's a correlation pattern here. In this particular model, there's not really, but in some models, you'll see a stronger correlation pattern. And you can kind of see how these different offsets vary between participants. You can also do this as a QQ type plot for these unbiased estimates. But I want to spend a little bit more time on a different type of plot, which we call a shrinkage plot. And this is an example from a slightly simpler model. The axes are the different variance components in a mixed model. So here we have the by participant intercepts on the x-axis and a by participant slope on the y-axis. The red dots are approximately what you get from an ordinary least squares fit within participants, approximately because that's not actually how we do that. And the blue dots are the conditional modes, so the BLUPs. And what you can see is what a mixed model actually does compared to classical regression. So you have this notion of shrinkage, this regularization, where the, individual data points are moved towards the population level estimates. And this is actually a good thing. Regularization and regression is a good thing. You might be thinking, okay, but is there more structure to this? And also, I'm claiming that they're being shrunk towards the population mean, but if you look, some of these points seem to get more outward on a certain axis. So for example, this participant here on the left might look like it's going out a little bit further. And so is there a better way we can visualize this? And the answer is yes. We can add in these correlation ellipses. So these are also curves of equal probability. And this is computed from the covariance structure of the mixed model. And so what you can actually see is that the points do move inward within a correlation ellipse. They move further inward. So they are actually getting into a better position. We can also use this type of plot to visualize excess dimensionality, so singular fits in mixed effects models. What you can see is that for this more complicated model, so we have all the pairs, that's why we have all the pairs, that for some of the variance components, things collapse down into a line. And this is actually indicative that this model is overly complex. And because of regularization, we can actually fit these overly complex models. But this also hints that our models are more complicated than they need to be. There's a big debate in the mixed models literature about how you should specify these things. And the answer is, from my perspective, is this is being collapsed down to one dimension. It's singular, so you don't actually need that dimension. And you can see for some things, it's actually collapsed down to a point. And you can also see the effect, for example, of constrained covariance structure. So in this case, we've constrained the covariance structure to be orthogonal, so to have zero correlation between these things, so that the covariance matrix is diagonal. And you can see that the shrinkage can only occur along perpendicular lines. And this is otherwise the same model as the previous plot. And you can actually see what constraining the covariance structure does to our ability to have efficient shrinkage. For example, in this panel, how that shrinkage looks compared to this panel. And so you can see that this constraint in the covariance structure, while it makes it easier to fit a model faster, actually really does have big impacts on what our estimates are. And finally, as I fly through my slides faster than I thought I was going to, I also want to highlight something that we took advantage of with Mach-E. And for mixedmodels.jl, we use a very nice profiled log likelihood to be able to evaluate these things very quickly and fit our models very quickly. And we use the Bobby-Quell optimizer from NLOpt to do this. And the likelihood in a mixed model is quadratic, or in a linear mixed effects model is quadratic. And it turns out that Bobby-Quell, which stands for bounded optimization by quadratic approximation, is very good at solving quadratic problems. And so on the bottom here, we have the different parameter values as the optimizer explores the parameter space. On the top, we have the objective, so deviance. And you can see that there's this initial broad exploration of the parameter space, and then the optimizer jumps to near the optimum. And it's nearly perfectly at the optimum. I want to leave time for one question at least, so I'm going to fast forward this recording. And you can see that actually the optimum or the log likelihood doesn't really change later, even though this one parameter value shifts a little bit. And this actually suggests something that we've implemented in a recent release, which is that you can reduce the convergence criterion when you're doing things like the parametric bootstrap, because it's better to have more replicates that are slightly worse than to have very few replicates that are exceptionally high quality. And that's it from me. I'm happy to take any questions. If not, then the next speaker has more time to set up their laptop. So I'm sure they'll appreciate that.
You also have time to think of questions. Yeah,
Okay. Feel free to file issues on Mixed Models Mach-E. Pop me a question on Slack or Zulip. We're always happy to have this out there. And for those of you who really care about the stats behind this, a longer, more detailed, and slower spoken version of this presentation will be presented at the joint statistical meetings in 2 weeks. Thank you.
Let's thank the speaker again. Connect your laptop. Feel free to set up. Yeah. All right, so I think we can get started. So our final short talk of the day is going to be on a modeling library for generalized dynamic systems.
Hello, everyone. My name is Emmanuel Lima, and I'm going to talk to you guys today about CAD-CAD-JL, a work-in-progress modeling library for generalized dynamical systems. So just a brief, who am I? My name is Emmanuel Lima, as I said. I am a senior research software engineer at Block Science, a R&D firm here based in the US. I am also the lead engineer for CAD-CAD, and I am a master's candidate in computer science at the University of São Paulo. Here's my email and my GitHub account in case any of you want to forward any questions after the presentation, in case you guys don't want to ask questions after the talk. So basically, what is CAD-CAD? So in a sentence, the objective of CAD-CAD is to orchestrate and simulate trajectories of generalized dynamical systems. What is exactly a generalized dynamical system? I will tell you guys in a bit. CAD-CAD stands for Complex Adaptive Dynamics Computer-Aided Design, and it's an open source framework for generalized dynamical systems. Currently, we have a reference implementation that is written in Python, and that reference implementation we use to give a form of a North Star for all future implementations of this library. And we are currently re-implementing the Python version of CAD-CAD in Julia, so hence CAD-CAD-JL. And of course, the main things that made us do the Julia switch were, as I think for many of other people from this conference, the performance gain that you get from Julia, of course, and the better type system. As I will explain a bit, the type system of Julia gives a much better edge when we implement CAD-CAD and we implement models with CAD-CAD. So basically, the why of CAD-CAD. Systems engineers, when they're going to do like model-based systems engineering, they usually use expensive proprietary software for that modeling, basically MATLAB and Simulink. And what we do with CAD-CAD is that we want to provide an open source and free alternative that plugs into the existing data science and data engineering pipelines that already exist, both in Python and in Julia. Our selling point is that the richness of the schema that you can make on the models that you can build with CAD-CAD can be arbitrary, whereas with MATLAB and Simulink, even like in addition for it to being proprietary, the schema is much more restricted because it generally is numeric. It's going to become clear on the next slides. So we have some use cases for CAD-CAD, for example, that we see right now. For example, we can engineer and validate complex systems. For example, you can use it to design digital twins. And specifically for those who are not accustomed with the term, a digital twin is a copy of a system that exists in real life, but inside of a computer. So you can control it, you can probe it, and you can simulate it. You could also do model-based, data-driven decision-making, or a live health monitoring when you have a live, real-time digital twin in the cloud, for example, where you can probe, you can change the parameters, and you can see what happens so you can make better predictions about your system. So basically, just in a brief note, what is a dynamical system? A dynamical system is a representation of a system that evolves over time, in a very brief sentence. That evolution can be entirely deterministic, or it can be subject to probabilistic events or influences. A typical dynamical system evolves, as you can see on the slide, a state x, given a function f, that will operate on that state x. So we have a set of all possible states that system can actually be, and that function f is going to walk over that possible state and is going to produce another point on that state and further the state over time. And the same thing goes for continuous dynamical systems. So the problem is with regular dynamical systems, the space, the structure that the system has is only a numerical one. With CAD-CAD, we use a generalized version of the theory called generalized dynamical systems, and the idea is to be able to evolve over time schemas that are not only numbers, but that have an arbitrary structure inside. So you can see that the structure has a form of a graph, and it can have any type inside it, not just numerical types. And you can evolve that schema over time. You can even have a meta model that will evolve the schema of a certain model over time, so you could have like a second order model with CAD-CAD. And as you can see, and this is why I said that on the transition from Python to Julia, it was very useful for us, the beta type system that Julia has, because we rely a lot on the type of the language to do type checking on the schema. So basically, we do evolutions of the time on the certain model by using the concepts of blocks. So blocks, as you can see, are the gray boxes. And the gray boxes are basically the container for the logic that is going to evolve the system over time. Those blocks, they can be seen as Lego pieces, and they can be joined together if they respect the little colored circles that are the spaces. The spaces are the schemas that I showed on the slide before, and they have a certain type signature that is that graph-like structure. So if I have a certain block whose codomain is equal to the following block domain, I can pipe together all of those blocks, meaning I can pipe together logics of making the system, or my digital twin, my model, go one step further in time. And by doing that repeatedly for n time steps, I can have a trajectory of my dynamical system for a generalized schema, not necessarily numeric. And we use block diagrams because we can have those properties. We can tear a pipeline of blocks, and we can analyze individual pieces of blocks together. We can zoom in on the pipeline, and we can simply look at a certain piece of that pipeline and focus on that. And we can link, meaning that all of those sub-pieces, individual blocks, or pieces of blocks together, they can be linked together because they are modular. So you can, just like a Lego, pierce together lots of different pipelines of blocks, and then create a very big pipeline, and then you can play with it as much as you want to create arbitrarily complex pipelines of blocks that simulate arbitrarily complex digital twins of arbitrarily complex dynamical systems. So that's it for me today. This is still a work in progress, both the Python version and the Julia version. And you guys can scan this QR code for some links. And if you guys want, you can join us. It's an open source project. It's a work in process, as I said. And we will be happy with any kind of help that we can get. Thank you very much.
Thank you very much again.
Thank you.
Yeah.